What if everything you see, the stars, the planets, the very screen in front of you, was born from a single, instantaneous connection? A connection so profound and bizarre that it defies our everyday logic, linking the birth of space and time itself in a cosmic handshake that set the entire universe in motion. This isn't just a poetic idea, it's a frontier of modern physics, and it all revolves around one extraordinary concept: the universe's first quantum entanglement. Think about that for a moment. Before galaxies, before atoms, before there was even a before, the cosmos may have begun with a fundamental act of linkage, a primordial bond where the fate of one particle was instantly and forever tied to another, no matter how far apart they flew. This is the event that might have kick-started everything, and today we are going on a journey to explore 30 mind-bending theories that attempt to explain this very phenomenon. We will venture from the fiery dawn of the Big Bang to the intricate weave of spacetime, uncovering how this initial spooky action at a distance could be the hidden engine behind it all. It's a story that connects the infinitesimally small quantum world to the breathtaking vastness of the cosmos, challenging not just what we know, but how we perceive reality itself. Imagine the universe in its first fleeting moments, a seething, hot, dense state where the laws of physics as we know them were still writing their first chapter. In that chaos, something miraculous occurred. According to some of the most brilliant minds in theoretical physics, the first quantum entanglement event didn't just happen within the universe. It may have been the act that created the universe, weaving the fabric of spacetime from a web of interconnected quantum information. This idea pushes the boundaries of our understanding, suggesting that the cosmos is not a collection of separate objects but a single, deeply interwoven whole. The entanglement that began then could be the reason why the universe has structure, why matter clumped together to form galaxies instead of spreading out into a thin, uniform haze. It might even hold clues to the emergence of consciousness, linking the quantum processes in our brains to the fundamental architecture of reality. This is not just science, it is a profound narrative about our origins, a tale written in the language of quantum mechanics that invites us to see ourselves as an integral part of this cosmic tapestry. So prepare to have your mind stretched. We are about to dive deep into a realm where time is malleable, where particles communicate faster than light, and where the very act of observation might shape existence. This journey will take us through ideas that are as beautiful as they are bizarre, from holographic universe principles to theories that suggest multiple realities branching from that first entangled state. You will discover how scientists are using this concept to explain the universe's accelerating expansion, the nature of black holes, and the mysterious dark energy that pervades the cosmos. Each of the 30 theories we explore is a piece of a grand puzzle, a step closer to understanding not just how the universe works, but why it is here at all. This exploration is for the curious, for those who look up at the night sky and feel a deep, resonating wonder. It's a journey into the heart of existence, and it all begins with that first mysterious quantum connection. To truly grasp this first theory, we need to rewind the cosmic clock all the way back to time zero. The Big Bang wasn't an explosion in space, but the very emergence of space and time from an unimaginably hot, dense point known as a singularity. In that first fleeting moment, all the forces of nature, gravity, electromagnetism, and the nuclear forces were fused into a single, unified superforce. It was within this primeval forge that the universe's first quantum entanglement is theorized to have been born. Picture the fabric of reality itself beginning to rapidly inflate, stretching from smaller than a subatomic particle to a macroscopic size in a fraction of a second. As spacetime expanded, it's thought that the first pairs of particles were created, locked together in an instantaneous quantum embrace. These weren't just any particles, they were the foundational seeds of everything to come, their fates intertwined from the very beginning. This initial act of entanglement offers a powerful solution to one of cosmology's oldest puzzles, the horizon problem. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see a universe that is remarkably uniform. The temperature is almost exactly the same in all directions, to within a tiny fraction of a degree. But according to the standard Big Bang model, there hasn't been enough time since the beginning for light or heat to travel from one distant region to another to even out these temperatures. It's as if you walked into a vast room where hundreds of people you've never met all independently decided to wear the exact same outfit. How could they have coordinated without communicating? The answer proposed by this theory is profound. Those distant regions of the universe were in contact, but not through any signal traveling through space. They were born connected, quantumly entangled in the first moments of the cosmos. Their shared properties were set at birth, and the subsequent inflation of the universe simply stretched that initial connection across vast cosmic distances. The implications of this are staggering. This primordial entanglement didn't just create uniformity, it may have also planted the seeds for all the structure we see today. The microscopic quantum fluctuations present in that initial singularity, now woven into the fabric of spacetime by entanglement, were stretched to enormous sizes during inflation. These tiny ripples of density became the gravitational wells where matter began to cluster. Over billions of years, those clusters grew through the relentless pull of gravity, eventually forming the first stars, galaxies, and the vast cosmic web that connects them. So, the grand tapestry of the cosmos, the majestic swirl of galaxies and the immense voids between them, might find its origin in a subatomic dance that occurred in the universe's first moment. The very spot where you are sitting right now was once quantumly linked to the most distant quasar, a connection forged in the fire of creation itself. Building directly on this idea of a deeply interwoven cosmos, the second theory takes interconnectedness to its ultimate extreme, proposing that our perception of a three-dimensional universe is in fact a magnificent illusion, a hologram. The holographic principle, a revolutionary concept born from the study of black holes, suggests that all the information contained within any volume of space can be perfectly described by bits of information stored on its two-dimensional boundary, much like a three-dimensional holographic image is encoded on a flat, two-dimensional piece of film. And what is the fundamental process that creates and sustains this intricate connection between the boundary and the bulk, between the cosmic film and the projected image? It is quantum entanglement. This theory posits that the very first quantum entanglement in the universe was the act that set up this holographic code, establishing the fundamental rule that every point within our reality is inextricably linked to a point on the cosmic horizon. To understand how bizarre and profound this is, think about a black hole. One of the biggest puzzles in physics has been what happens to information when matter falls into a black hole. The laws of quantum mechanics insist that information can never be truly destroyed, but a black hole's immense gravity seemingly swallows it whole. The holographic principle offers a stunning solution. It suggests that all the information about the objects that have fallen in is not lost inside the singularity but is instead perfectly preserved, encoded on the black hole's two-dimensional event horizon, the point of no return. The entanglement between quantum particles on the horizon and the interior of the black hole is what allows this information to be stored and retrieved. Now scale this idea up to the entire cosmos. Our universe, with its three spatial dimensions, could be a vast holographic projection from a two-dimensional shell at the very edge of the observable universe. That first primordial entanglement event was the moment this cosmic projector was switched on, weaving the threads that connect every star, every planet, and every one of us to a distant fundamental surface. This provides a radical new perspective on the nature of spacetime itself. We typically think of space and time as the fundamental stage upon which the drama of the universe plays out. But the holographic principle powered by entanglement turns this notion on its head. It suggests that spacetime is not fundamental at all. Instead, it is an emergent property, a collective phenomenon that arises from the complex web of quantum entanglements between countless microscopic degrees of freedom on the boundary. It's analogous to the temperature of a gas. We can measure a single temperature, but that property doesn't belong to any one atom. It emerges from the collective, frantic motion of trillions of atoms. In the same way, the smooth, continuous geometry of spacetime emerges from the intricate quantum connections at the universe's edge. The first entanglement was the seed from which the very concepts of here and there and before and after grew, crystallizing into the reality we experience. This means that every step you take, every breath you draw, is a direct consequence of that initial, universe-defining quantum link, a connection so fundamental that it literally constructs the space around you. If the holographic principle suggests that space itself is a projection, then where do the patterns for that projection come from? This brings us to a pivotal moment in cosmic history, the era of inflation, and a theory that describes it not just as a stretching of space, but as a great entanglement generator. The cosmic inflation entanglement burst theory proposes that the universe's hyper-expansion did far more than simply make the cosmos larger. It acted as a cosmic loom, weaving a foundational web of quantum connections that would dictate the future structure of everything. During this incredibly brief period, the universe expanded by a factor of trillions upon trillions in a mere sliver of a second. And within that violent, exponential stretching, the quantum field that drove the process, the inflatoned field, was itself fluctuating. These weren't mere random jitters. According to this theory, these fluctuations became quantumly entangled with one another on a scale that was once microscopic, but was suddenly blown up to a size encompassing the entire observable universe. Think of it like this. Imagine two tiny, interconnected particles existing in a volume of space smaller than an atom. In our normal, slow-moving world, they might drift apart over time, their connection stretching but remaining. Now imagine that the space between them is suddenly inflated faster than the speed of light. The distance separating them becomes astronomically vast in an instant, but their quantum connection, their entanglement, does not break. It is simply stretched across the newborn cosmos. This is precisely what the theory suggests happened during inflation. Countless pairs of particles, or more accurately, fluctuations in the inflatoned field, were born entangled. As the universe inflates, these partners are pulled apart to incredible distances, yet they remain mysteriously linked. When inflation finally ended, its energy decaying to create the hot soup of particles of the Big Bang, this vast, frozen network of entanglement was imprinted directly onto the fabric of reality. The most stunning evidence for this idea is written across the entire sky. The cosmic microwave background radiation, that ancient light from when the universe was only 380,000 years old, is not perfectly smooth. It contains tiny variations in temperature, minuscule hot and cold spots that form a specific pattern. According to the inflation entanglement burst theory, these patterns are the direct, fossilized imprint of those primordial quantum fluctuations. The hot spots correspond to regions of slightly higher density in the early universe, and the cold spots to regions that were slightly more sparse. But here's the crucial part. The statistical properties of these temperature fluctuations, the way they correlate with each other across the sky, match the predictions for what you would expect if they originated from a vast field of entangled quantum fluctuations. It's as if we are looking at a baby picture of the universe and seeing the ghostly signature of its first quantum connections. This provides a breathtakingly direct link between the quantum world and the cosmic scale. Those infinitesimal quantum ripples, magnified by inflation and locked in place by entanglement, became the gravitational seeds for the entire cosmic web. Over billions of years, gravity acted on these initial density variations, pulling more and more matter into the slightly denser regions. the subtle hills and valleys in the fabric of the universe, set by that initial burst of entanglement, grew into the great clusters of galaxies, the long filaments of dark matter, and the vast empty voids that we observe with our telescopes today. So, the majestic architecture of the cosmos, from the largest supercluster to the local group of galaxies that includes our Milky Way, may have its ultimate origin in a quantum phenomenon that played out in the first trillionth of a second. The universe's first entanglement burst didn't just create a uniform backdrop. It provided the detailed blueprint for everything that was to come, a blueprint we are still decoding in the faint whisper of the microwave sky. While the previous theories paint a picture of entanglement woven into the fabric of spacetime itself, what if the first connections were far more tangible, born within the most extreme objects the universe can produce? This leads us to a truly captivating idea, the primordial black hole network. Imagine the universe not even a second old, a seething, chaotic broth of energy where the density was so unimaginably high that random fluctuations could cause pockets of space to collapse under their own gravity. These wouldn't be the stellar mass black holes born from dying stars. These would be microscopic, quantum-scale black holes popping in and out of existence in the furious energy of the cosmos's birth. According to this hypothesis, it was within this frenzied environment that the universe's first stable quantum entanglements were forged, not between simple particles, but between these infinitesimal black holes. The concept is as elegant as it is profound. When two such primordial black holes form in close proximity, perhaps from a single quantum fluctuation, the laws of physics suggest they could become intrinsically entangled. Their properties, their spin, their mass, their very quantum states will be linked instantaneously. Now, picture this process happening not just once, but countless times across every cubic centimeter of the infant universe. The result would be a vast, intricate, and subatomic web, a cosmic network where each node is a tiny black hole connected to many others through quantum threads. This wouldn't be a static network, it would be dynamic and interactive. As these black holes evolved, merged, or evaporated via Hawking radiation, their entangled connections would be transferred, broken, and reformed, creating a constantly shifting tapestry of quantum information. This leads to one of the most staggering implications of this theory. This network could have acted as the universe's first and most fundamental quantum computer. A quantum computer works by using entangled qubits to perform calculations in ways that are impossible for classical computers. The primordial black hole network, with its countless entangled nodes, would have been a natural, cosmic-scale quantum processor. It would have been constantly processing the information of the universe itself, potentially running the code that dictated how matter would eventually clump together. The complex patterns of galaxies and the cosmic web we see today could be the frozen output of computations that occurred in the first fraction of a second after the Big Bang, a cosmic program executed by a network of entangled black holes. Perhaps the most compelling application of this idea is its potential to solve one of cosmology's greatest mysteries, the nature of dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have never directly detected what it's made of. The primordial black hole network offers an elegant candidate. This vast, unseen web of microscopic black holes woven through the entire cosmos would have mass and would not interact with light, perfectly matching the observed properties of dark matter. They would be the hidden architecture, the cosmic scaffolding that guided the formation of the first galaxies. Their gravitational influence, combined with the quantum information processing of their network, could provide the precise conditions needed for the universe to evolve the rich structure we observe, offering a unified explanation for two profound puzzles. This theory also provides a crucial bridge between the two great pillars of modern physics, quantum mechanics and general relativity. Black holes are the only objects in the universe where these two theories meet head-on and where both break down. A primordial black hole, by its very nature, is a quantum gravitational object. Therefore, studying the entanglement between them gives us a unique window into how gravity behaves at the quantum scale. The way information is shared and preserved across this network could hold the key to a theory of quantum gravity, finally revealing how the force that shapes the cosmos emerges from the fuzzy quantum world. In this view, the first quantum entanglements were not a side effect of the Big Bang, but the foundational elements of a computational matrix that calculated the destiny of the cosmos, with the dark matter that binds our galaxies being the enduring relic of that ancient entangled web. Now, if you thought the idea of a black hole network was mind-bending, prepare for a concept that ties together two of Einstein's most famous and seemingly contradictory legacies. We arrive at a theory so elegant and profound that it feels like a key clicking into a cosmic lock, the ER equals EPR conjecture. This revolutionary proposal, championed by physicists Juan Maldacena and Leonard Susskind, boldly states that the phenomenon of quantum entanglement and the existence of wormholes are not just related. They are one and the same thing, described in two different languages. Let's break that down. On one side, you have EPR, named for Einstein, Podolsky, and Rosen, who first highlighted the spooky action at a distance of quantum entanglement, where two particles share a single fate regardless of the miles between them. On the other side, you have ER for Einstein and Rosen, who theorized the bridges in spacetime we call wormholes, hypothetical tunnels offering a shortcut between two distant points in the universe. The conjecture asserts that these are not separate ideas. An entangled pair of particles is in fact connected by a microscopic wormhole. They are two sides of the same cosmic coin. This has a breathtaking implication for the origin of the cosmos. If we apply this logic to the universe's first quantum entanglement, it suggests that event didn't just create a spooky link. It literally forged the first tiny wormhole, stitching together the very fabric of spacetime in that initial moment. Imagine the newborn universe as a collection of disjointed points. With each new quantum entanglement, a new microscopic bridge is formed, linking one point to another. As more and more of these entanglements occurred, more wormholes were woven into existence, connecting every point to its neighbors until a vast, coherent, and continuous fabric of space emerged. In this view, the distance between two stars isn't just empty space. It's a landscape built from an incalculable number of these tiny, woven connections. The connectivity of space is not a given. It is a direct manifestation of the universe's underlying quantum entanglement. To grasp the sheer power of this idea, consider one of the biggest headaches in modern physics, the black hole information paradox. When something falls into a black hole, does the information about that object vanish forever when the black hole eventually evaporates, violating quantum law? The ER equals EPR conjecture offers a stunningly elegant solution. Imagine two entangled particles. One falls into a black hole while its partner remains outside. According to the old view, the connection is severed and information is lost. But according to this new picture, the two particles are connected by a wormhole. The particle that falls in isn't lost. Its information travels through the microscopic wormhole and is preserved in its entangled partner on the outside. The black hole's interior is secretly connected to the outside universe through a web of these wormholes, ensuring that no information is ever truly destroyed. This resolves the paradox by showing that entanglement provides a hidden pathway for information to escape, preserving the sacred laws of quantum mechanics. This conjecture's greatest promise may be its potential to finally unite the two great conflicting theories of physics, quantum mechanics and Einstein's general relativity. For decades, these two frameworks have described the universe with brilliant accuracy, but they are fundamentally incompatible. Quantum mechanics rules the tiny world of particles with probability and uncertainty, while general relativity describes the grand cosmos of gravity and spacetime as a smooth geometric fabric. ER equals EPR acts as a cosmic translator. It tells us that the weird, non-local connections of quantum entanglement are, in fact, the geometric threads of spacetime itself. The force of gravity and the geometry of the universe may not be fundamental, but could instead emerge from this vast, underlying network of quantum connections. It suggests that if we could ever peer down to the smallest possible scale of reality, the Planck scale, we wouldn't see a smooth continuum. We would see a seething, foamy network of wormholes, a spacetime built from quantum handshakes. This fundamentally redefines our understanding of distance and separation. In our everyday lives, we think of two objects as being far apart because there is a literal, physical expanse between them that we must traverse. But if ER equals EPR is correct, then distance is an illusion born from a lack of connectivity. Two points that are entangled are, in a very real geometric sense, close together because they are connected by a wormhole, a shortcut through the architecture of reality. The most distant galaxy and the screen in front of you were once quantumly entangled in the early universe, and in that sense, they remain intimately linked through the hidden geometry of spacetime. This turns our perception of the cosmos inside out, suggesting that the universe is far more interconnected than we ever dreamed, with every part holding a secret, direct line to every other part, a cosmic unity written into the very laws of physics. But if the universe did begin with a single, definitive Big Bang, we are left with a perplexing question. Why did it start in such a remarkably ordered state? This is the puzzle of low entropy, and it leads us to a theory that completely reimagines the very nature of time and cosmic beginnings. Enter the concept of the cyclic universe, a model where the Big Bang was not a true beginning, but merely a pivotal moment of transition, a cosmic rebound from a prior phase of collapse. In this breathtaking vision of eternity, the universe undergoes an endless, rhythmic dance of expansion and contraction, a series of cosmic cycles with no start and no end. And within this grand perpetual motion, the first quantum entanglement of our universe takes on a profound new meaning. It wasn't a spontaneous creation, but a precious inheritance, a legacy passed directly from the dying embers of the previous cosmos. To grasp the weight of this idea, we need to understand entropy, which is essentially a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Think of a hot cup of coffee left on a table. It will eventually cool down to room temperature, moving from a state of concentrated heat to a more diffuse, disordered state. It will never spontaneously heat up again on its own. Now, apply this to the entire universe. Our cosmos today is a messy, complex place with stars burning out and black holes forming, a state of relatively high entropy. But when we look back to the moment of the Big Bang, we find a universe that was incredibly hot and dense, yet also incredibly smooth and uniform. This is a state of astonishingly low entropy, like a pristine, unbroken egg. It's the ultimate cosmic puzzle. Why did the universe start in such a highly ordered, unlikely condition? A single, one-off Big Bang offers no clear answer. The cyclic universe model provides an elegant solution. Imagine the previous cosmic cycle. It expanded for billions of years, just as ours is doing now, before the collective pull of gravity and dark energy finally reversed its course, leading to a big crunch. In this final phase, all matter and energy are compressed into an unimaginably hot, dense state. However, according to this theory, not everything is erased. While atoms are torn apart and even space-time is stretched to its limits, certain quantum information is indestructible. The intricate web of quantum entanglement that had woven the previous universe together, the connections between countless particles, somehow survives the collapse. They are not wiped clean, as the old universe contracts to its maximum density and then rebounds in a new Big Bang. these entangled connections are imprinted directly onto the newborn fabric of the new cycle. They become the foundational seeds, the cosmic DNA that dictates the initial low entropy state and the specific patterns of fluctuation for the next universe. The smooth, ordered beginning of our universe isn't a mysterious starting point. It's the natural consequence of being born from the refined, compressed ashes of its predecessor. This transforms the nature of quantum information from a transient phenomenon into something potentially eternal. In a single bang universe, all quantum information is created at the beginning and may ultimately be lost in the heat death of eternal expansion. But in a cyclic cosmos, quantum entanglement becomes a cosmic constant, a thread of connectivity that weaves its way through each cycle, preserving a kind of memory from one incarnation of reality to the next. The specific entangled pairs that we might observe today between distant quasars could, in principle, have their origins in a universe that existed trillions of years before our own. Their connection has persisted through a fiery collapse and a glorious rebirth, a timeless bond that transcends the life and death of individual cosmic epochs. This offers a radical new perspective on the arrow of time itself. The reason time has a direction why we remember the past but not the future might be because each new cycle inherits a low entropy state from the one before, setting the clock ticking once more in the same direction. Several specific models bring this poetic idea into rigorous mathematical focus. One prominent version is the conformal cyclic cosmology proposed by the renowned physicist Roger Penrose. In his model, the universe doesn't end in a violent crunch, but in a vastly expanded cold state where all particles have decayed and black holes have evaporated. At this extreme endpoint, the universe loses all sense of scale. There is no meaningful distinction between large and small. Penrose proposes that this infinitely expanded, featureless state can be mathematically identified with the high-energy, featureless state of the next Big Bang. In this transition, the information is preserved and remapped, allowing for a form of cosmic inheritance. While the specifics are intensely debated, the core idea resonates. The universe may be in a constant state of renewal, with quantum information, including entanglement, acting as the immutable thread connecting each iteration. This theory also provides a fascinating potential link to one of the most mysterious forces in the cosmos, dark energy. The observed acceleration of the universe's expansion is driven by this enigmatic energy. In a cyclic model, dark energy might not be a fixed constant but a field that evolves over eons. It could be the very agent that eventually halts the expansion and initiates the next contraction, setting the stage for the next bounce. The behavior of this field and how it interacts with the surviving web of entanglement during the bounce could determine the fundamental constants and laws of the subsequent cycle. Perhaps the strength of gravity, the mass of an electron, or even the number of spatial dimensions in our universe are not arbitrary, but were subtly shaped by the quantum information carried over from the previous cycle. This suggests a form of cosmic evolution, where the laws of physics themselves could slowly refine over countless cycles, with quantum entanglement serving as the mechanism of inheritance. Our universe, with its specific conditions that allow for stars, planets, and life, might not be a random accident, but the latest outcome in an infinite series of cosmic generations, each one building upon the quantum legacy of the last. Shifting our perspective from a single, cyclical cosmos to an almost unimaginable vastness of realities, we arrive at a theory that fundamentally redefines the meaning of the universe. This is the multiverse hypothesis, and within its staggering framework lies a radical proposal. The first quantum entanglement in our cosmic story was not a domestic affair. It was an international event, a brief but profound handshake reaching across the void to a completely separate universe. In this mind-bending scenario, a particle in our own nascent cosmos became inextricably linked with a particle in a neighboring bubble universe, an event that broke the symmetry of creation and set our reality on its unique evolutionary path. To understand how such a cross-universe connection could even be possible, we need to explore the concept of eternal inflation. Picture the greater cosmos not as a single entity, but as an infinite bubbling foam. The fundamental energy field that drives this process is constantly boiling, and within this seething substrate, pockets of lower energy can randomly form. Each of these pockets stops inflating internally and crystallizes into its own distinct universe, with its own random set of physical laws and constants. Our entire observable universe is just one such bubble in an endless, frothing sea of other universes. Now, according to this theory, in the fleeting moments when two such bubbles are born in close proximity, their boundaries can briefly touch or overlap before they are forever driven apart by the relentless inflation of the space between them. It is during this ephemeral contact that a particle or a quantum field fluctuation on our side could have become entangled with its counterpart on the other. This wasn't a connection through space as we know it, but a connection between spaces, a quantum bridge linking two separate realities. The implications of this initial crosstalk are nothing short of revolutionary for our understanding of why our universe is the way it is. The fundamental constants of nature, the strength of gravity, the mass of an electron, the force that binds atomic nuclei, appear to be exquisitely fine-tuned for the existence of complex matter and life. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, galaxies and stars would never have formed. This fine-tuning problem has long perplexed scientists. The multiverse entanglement theory offers a compelling explanation. Our universe did not win a cosmic lottery. Instead, its specific laws were influenced or even selected by that first external connection. The act of entangling with a neighboring universe could have broken the perfect symmetry of our bubble's birth, tipping the scales and locking in the specific values for the constants we observe today. Our universe's life-friendly properties might not be a lucky accident, but the consequence of a conversation with another reality. This leads to one of the most exciting prospects in modern cosmology, the potential to detect evidence of the multiverse. If our universe was once entangled with another, that connection, though stretched across an unimaginable gulf, would leave a lasting imprint. The laws of quantum mechanics tell us that measuring one particle of an entangled pair instantly affects its partner, no matter the distance. While we cannot travel to another universe to check, the echoes of that primordial interaction might be frozen into the oldest light we can see, the cosmic microwave background. Physicists have speculated that a collision between our bubble universe and another would create a distinct anisotropic pattern, a kind of bruise on the sky. Furthermore, the specific statistical properties of the quantum fluctuations imprinted in that light could bear the signature of that initial cross-border entanglement. We are, in effect, searching for a cosmic fingerprint left by a foreign reality, a ghostly scar that whispers of our connection to an infinite family of other universes. This theory also provides a fascinating new perspective on the nature of quantum weirdness itself. The famous, spooky action at a distance that so troubled Einstein becomes even spookier when the entangled particles don't just reside in different galaxies, but in different universes altogether. It challenges our deepest notions of locality and reality, suggesting that the quantum connections that bind particles together are not constrained by our local spacetime. They operate on a deeper, more fundamental level, a substrate from which individual universes emerge. In this view, the multiverse is not merely a collection of disconnected bubbles. It may be subtly, quantumly intertwined at its most fundamental level. The first entanglement in our history was therefore a tap into a pre-existing, vast network of cosmic crosstalk, a network that may still be active today, with threads of connection weaving through the multidimensional foam in ways we are only beginning to imagine. So far, we've explored universes born from collisions, cycles, and holograms, but what if the ultimate origin is even more fundamental, emerging from absolute nothingness? This brings us to a theory that pushes the very limits of physics and philosophy, the timeless void fluctuation. Picture this, not a seething plasma, not a cosmic egg, but a true void, a state of perfect, metastable nothingness. No space, no time, no matter, no energy, just a pure, unmanifested potential. According to this profound idea, our entire cosmos began as a random jitter in this void, a quantum fluctuation so monumental that it didn't just create a particle, but it birthed the very framework of reality. In this timeless realm, the rules of quantum mechanics suggest that something can, and indeed must, come from nothing. Particles and antiparticles can spontaneously pop into existence, borrowing energy from the vacuum for an infinitesimally brief moment before annihilating each other and paying back the debt. The theory posits that one such fluctuation didn't flicker out. Instead, it was a fluctuation of a different order, one that created a pair of particles that were intrinsically, irrevocably entangled. This wasn't an event in time. It was the event that created time, with the first tick of the cosmic clock being the moment this entangled pair sprung into being, establishing the first two reference points for what would become spacetime. The philosophical implications of this are staggering. It suggests that the universe is, in a very real sense, a free lunch. The total energy of the cosmos is likely zero when you account for the positive energy of matter and the negative energy of gravity binding it together. This entire vast, complex existence could have a net value of nothing, originating from a random ripple in the void that simply persisted. This aligns beautifully with the principle of quantum indeterminacy, which states that empty space is never truly empty. It's a foaming, bubbling sea of virtual particles constantly appearing and disappearing. The birth of our universe, then, was not a unique miracle, but the one fluctuation that managed to stabilize, inflate, and evolve into everything we know. Our reality is the ultimate lottery winner, the one in an infinity chance that took hold and grew. This elegantly sidesteps the problem of an infinite regress, what created the creator, by proposing that the universe created itself from nothing, with quantum mechanics providing the necessary mechanism. There is no before the Big Bang because time did not exist. The fluctuation was the beginning of time, a singular pivot from eternal stillness into dynamic becoming. This radical perspective forces us to reconsider the very nature of time. In our daily lives, we experience time as a relentless, flowing river, carrying us from the past into the future. But in the framework of fundamental physics, particularly in certain interpretations of quantum mechanics, time may not be a fundamental ingredient of the universe. Theories like the Wheeler-DeWitt equation, an attempt to merge general relativity with quantum mechanics, famously describe a static universe without time. The flow of time, in this view, could be an emergent property, a psychological or thermodynamic illusion that arises from the complex correlations between quantum events. The timeless void fluctuation theory gives this abstract idea a concrete origin story. The first quantum entanglement between those two primordial particles established the first correlation, the first before and after. The act of one particle influencing the other, even in that timeless void, created a sequence, a relationship that became the prototype for causality. Time, as we perceive it, emerged from that first quantum handshake, crystallizing from a state of pure being into a framework of becoming. To make this abstract concept more tangible, consider an analogy from computing. Imagine a computer in a powered-off state. The screen is blank and no processes are running. It is static and timeless. Now, a single electrical fluctuation occurs within a transistor, a random bit flip from a 0 to a 1. This single event triggers a cascade. Other bits flip in response, circuits activate, and the boot-up sequence begins. The computer's internal clock starts ticking, and time, from the computer's perspective, begins. The entangled particle pair from the void is akin to that first bit flip. Their correlated existence broke the perfect symmetry of nothingness and initiated the boot-up sequence for the cosmos. The rapid inflation of the universe was that cascade, and the arrow of time we experience is the ongoing execution of that initial program. This view is supported by the way we observe quantum entanglement operating even today, seemingly instantaneously, outside of our normal conception of time, hinting at a deeper, timeless layer of reality from which our temporal world emerges. The theory also offers a fresh and compelling interpretation of the universe's initial conditions. Why was the early universe so incredibly uniform and flat? In the standard Big Bang model, this requires a finely tuned initial state, another puzzle. But if the universe began as a single quantum fluctuation, its properties were dictated by the laws of quantum mechanics. A fluctuation from a featureless void would naturally produce a state that is smooth and symmetric. The tiny quantum ripples that eventually seeded galaxies were simply the inherent uncertainties of that initial fluctuation, magnified to cosmic scales. This provides a natural, rather than a miraculous, explanation for the universe's startling order at its inception. It suggests that the cosmos we see is a direct and logical consequence of the fundamental rules governing reality at its most basic level, with the first quantum entanglement serving as the cosmic seed from which all of space, time, and matter would eventually grow. We are not just living in the aftermath of a giant explosion, but we are the evolved, complex expression of a single, timeless quantum event, a connection that forged existence itself from the quietest whisper of the void. Yet, if the universe was born from a timeless void, what were the fundamental rules that allowed such a profound transition? This brings us to the very heart of modern theoretical physics and a theory that seeks to answer the ultimate question. How did gravity, the force that sculpts the cosmos, behave when the universe was at its smallest possible scale? We now arrive at the quantum gravity genesis, a compelling proposal that the very first quantum entanglement wasn't between particles of matter or energy, but between the fundamental quanta of gravity itself. To understand this, we must venture back to the Planck epoch, the first sliver of cosmic time, a period so brief it defies imagination, just 10 to the minus 43 seconds after the Big Bang. At this moment, the entire observable universe was compressed into a volume far smaller than a single atom, a realm where the classical, smooth spacetime described by Einstein's general relativity completely breaks down. In this quantum foam, gravity was not a gentle curvature but a wildly fluctuating, granular force. This theory posits that the first stable structures to emerge from this chaos were the elementary grains of spacetime, and that these grains became quantumly entangled, an event that effectively programmed the entire geometric destiny of our cosmos. The quest to describe this epoch is the holy grail of physics, a theory of quantum gravity. For decades, our two most successful frameworks have been locked in a stalemate. Quantum mechanics, with its probabilities and uncertainties, exquisitely describes the behavior of particles and forces on the smallest scales. General relativity, with its smooth, geometric fabric of spacetime, masterfully explains the large-scale structure of the universe and the force of gravity. Yet, they are fundamentally incompatible. Quantum gravity is the long-sought framework that would unite them, and two leading candidates, loop quantum gravity and string theory, offer different but equally fascinating pathways to understand that first gravitational entanglement. Loop quantum gravity proposes that space itself is not continuous, but is woven from a network of finite, one-dimensional loops. Think of the fabric of reality as a tapestry made of individual threads. At the Planck scale, these loops form a dynamic, evolving lattice, and their intersections represent the smallest possible units of volume. In this picture, the first quantum entanglements were the connections between these loops, weaving the very first stitches of the spatial fabric. The way these loops became linked and correlated dictated how space could curve and evolve, setting the stage for the expansion we observe today. String theory, on the other hand, approaches the problem from a different angle. It proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we see, including the graviton, the hypothetical quantum particle that carries the gravitational force. In the dense frenzy of the Planck epoch, these strings and their higher dimensional counterparts called branes would have been colliding and interacting constantly. The quantum gravity genesis theory within string theory suggests that the first entanglement occurred between these fundamental strings, particularly between the gravitons they produced. When two gravitons became entangled, their connection established a correlation in the geometry of spacetime they were destined to create. This initial gravitational handshake then propagated, influencing how subsequent gravitons interacted, effectively coding the gravitational field and the very rules of geometry into the universe from its very first moment. One of the most profound implications of this idea is its potential to explain the origin of the arrow of time. Why does time have a distinct direction, always flowing from the past to the future? The laws of physics themselves are mostly time-symmetric. They work just as well if time runs backwards, yet we never see a shattered cup reassemble itself. This one-way street is described by the second law of thermodynamics. The universe's entropy or disorder always increases, but why was entropy so low to begin with? The quantum gravity genesis offers an elegant solution. In the framework of loop quantum gravity, for instance, the initial state of the universe is a highly ordered, low-entropy state because the quantum geometry was maximally entangled. The intricate web of connections between the spacetime loops represented a state of high order. As the universe expanded and cooled, this web evolved and simplified, with some connections decohering or breaking. This process of moving from a highly connected, ordered geometric state to a less connected, more disordered one is what we experience as the forward march of time. The arrow of time, therefore, may not be a fundamental law but an emergent property, a direct consequence of the universe's spacetime geometry unwinding from its initial, perfectly entangled state. This gravitational programming also provides a natural mechanism for the creation of the large-scale structure we see. The microscopic quantum fluctuations in the gravitational field, the tiny wobbles in those first entangled spacetime grains or strings, were stretched to astronomical sizes during the period of cosmic inflation. These fluctuations in gravity directly translated into fluctuations in the density of matter and energy. Where the gravitational field was slightly stronger, more matter was pulled in, eventually forming galaxies and clusters. Where it was slightly weaker, vast cosmic voids emerged. The specific pattern of the cosmic web, the great walls of galaxies and the empty tracts between them, is therefore a frozen record of the quantum gravitational fluctuations that were present at the universe's birth. Fluctuations that were correlated and amplified by that initial act of entanglement. When we map the distribution of galaxies across the sky, we are, in a very real sense, reading the original geometric code written by the first entangled gravitons. Exploring this theory pushes the very limits of our experimental capabilities, as we cannot directly probe the Planck epoch. However, scientists are searching for indirect signatures. One promising avenue is the study of the cosmic microwave background polarization. The gravitational waves generated by the violent processes in the very early universe would have left a distinct swirling pattern known as B-mode polarization on this ancient light. Detecting this primordial gravitational wave signal could provide a direct window into the conditions of the Planck epoch and the behavior of quantum gravity. Furthermore, by analyzing the statistical properties of these signals, physicists hope to find hints of the non-local correlations that are the hallmark of quantum entanglement. Another frontier is the study of black holes, where quantum gravity effects are expected to be paramount. The way information escapes a black hole, as suggested by the ER equals EPR conjecture, relies on entanglement, and understanding this process fully will require a theory of quantum gravity. Each of these investigations brings us closer to verifying whether the geometry of our reality, the force that holds our feet to the ground and guides the planets in their orbits, was indeed born from a cosmic code written in the language of entangled quantum gravity. As we navigate these theories linking the quantum realm to the cosmic scale, we inevitably confront one of the most profound and enduring mysteries, the nature of consciousness itself. This brings us to a deeply speculative yet utterly captivating frontier, the consciousness-cosmology link. This theory ventures where few dare, proposing that the universe's first quantum entanglement was not merely a physical event, but the dawn of a shared experience, a primordial act of connection within a field of universal proto-consciousness. The idea rests on a philosophical stance known as panpsychism, which suggests that consciousness is not an emergent property of complex biological brains alone, but a fundamental and ubiquitous feature of the cosmos, inherent in even the most basic forms of matter. In this view, electrons, photons, and the very fabric of spacetime itself possess a minute degree of subjective experience or mentality. The first quantum entanglement, then, was the moment two such primitive conscious entities first linked their inner worlds, creating the most elementary form of a shared reality. The driving force behind this theory is the desire to solve the hard problem of consciousness. This is the puzzle of why and how physical processes in the brain, the firing of neurons and the flow of chemicals, give rise to subjective first-person experience. The redness of red, the feeling of warmth, the sensation of being. Materialist science has struggled to explain how objective matter generates subjective qualia. Panpsychism offers a radical solution. It doesn't. Instead, consciousness was here first, woven into the fundamental building blocks of reality. When those first particles became entangled in the early universe, it wasn't just their spins or positions that became correlated. It was their infinitesimal inner perspectives that merged, however simply. This initial connection could be seen as the universe's first rudimentary thought, or the first step toward the complex, integrated consciousness we experience today. Proponents argue that this provides a seamless narrative for the evolution of mind, from the first quantum connection to the sophisticated awareness found in humans, suggesting that we are the universe becoming awake and aware of itself through an unbroken chain of increasingly complex entanglements. To make this abstract concept more relatable, consider an analogy with a digital image. A single pixel on a screen carries a tiny amount of information, a single point of colored light. On its own, it means very little, but when millions of these pixels become entangled in a specific correlated pattern, they give rise to a rich, meaningful picture that tells a story and evokes emotion. In the panpsychist view, each elementary particle is like a single pixel of consciousness. Its individual experience is unimaginably simple and foreign to us. But when particles become entangled, their conscious pixels link up. As these connections multiplied and grew in complexity throughout cosmic history, forming atoms, molecules, stars, planets, and eventually neural networks, the integrated conscious experience became richer and more complex, eventually culminating in the full-color movie of human awareness. The first entanglement was the moment the first two pixels synchronized, setting the precedent for the entire cosmic tapestry of mind to follow. However, this theory faces significant and formidable criticism from the mainstream scientific community. The most common objection is the combination problem. If every electron has a sliver of consciousness, how do billions upon billions of these micro-experiences combine to form the unified, seamless stream of consciousness you are having right now? It seems as mysterious as explaining how 1,000 random whispers in a crowd could combine to produce a single, coherent symphony. Critics argue that panpsychism doesn't so much solve the hard problem as it relocates it, pushing it down to the level of fundamental physics without providing a clear mechanism for combination. Furthermore, the theory is often accused of being non-falsifiable. It's difficult to imagine an experiment that could prove or disprove that an electron is conscious. Without a clear path to experimental verification, it risks residing in the realm of philosophy rather than empirical science. Despite these challenges, the theory finds intriguing, if indirect, support from certain interpretations of quantum mechanics itself. The famous measurement problem, why quantum possibilities collapse into a single definite reality only when observed, has led some physicists, like John von Neumann and Eugene Wigner, to propose that consciousness plays a fundamental role in collapsing the wave function. While this is a minority view, it creates a conceptual bridge between mind and quantum reality. Additionally, the integrated information theory developed by neuroscientist Giulio Tononi provides a mathematical framework for consciousness that is not inherently tied to biology. It proposes that any system with a high degree of integrated information, known as phi, has consciousness. This could, in principle, apply to any sufficiently complex and interconnected system, from a human brain to a sophisticated computer network, and perhaps on a fundamental level to the web of entangled particles that constitutes the universe. This framework allows us to think of the cosmos not as a dead mechanical clockwork, but as a living, thinking entity in a very real mathematical sense, with its first entangled connection marking the moment its cognitive life began. This perspective forces a dramatic re-evaluation of our place in the cosmos. If the consciousness-cosmology link holds any truth, then human consciousness is not a fleeting accident in an indifferent universe. We are not separate observers looking in from the outside. Instead, we are localized knots of intensified awareness within a vast, already sentient cosmos. Our deepest thoughts, our creativity, and our sense of wonder are not anomalies. They are expressions of the universe's own inherent nature, refined and amplified through billions of years of evolution. The first quantum entanglement becomes more than a physical curiosity. It is the genesis of a relationship, the first moment the universe began to know itself. This idea, while currently on the fringes of science, challenges us to see the cosmos as intrinsically meaningful, a unified whole where mind and matter, the observer and the observed, have been partners in a grand cosmic dance since the very first moment of connection. But while the earliest moments of the cosmos were a frenzy of creation, the story of its structure depends heavily on an invisible protagonist. This brings us to an idea that places the universe's first quantum entanglement not in the spotlight but in the shadows, literally. The dark matter entanglement seed theory proposes that the very first stable quantum link was forged between particles of dark matter, the mysterious substance that makes up over 85% of the universe's mass yet refuses to interact with light. In this scenario, the most significant event in cosmic architecture was an invisible handshake between entities we have never directly seen. The leading candidates for these particles are known as WIMP, or weakly interacting massive particles and actions, which are theorized to be incredibly light and abundant. Both are thought to have been created in the hot, dense plasma of the very early universe. However, because they interact so feebly with normal matter and radiation, they would have decoupled or stopped interacting with the cosmic soup extremely early on, leaving them free to evolve according to their own rules. The theory suggests that in that brief window before decoupling, some of these dark matter particles became quantumly entangled. As the universe expanded and cooled, these particles were flung apart, but their entangled connection remained, creating a vast, invisible web of quantum correlations that stretched across the cosmos. This primordial dark matter network then became the universe's fundamental scaffolding. Long before the first atoms of hydrogen even formed, this web of entangled dark matter began to dictate the destiny of all structure. Gravity, acting on the dark matter, caused it to clump preferentially along the lines of its initial quantum connections. Think of it like a three-dimensional blueprint made of interconnected nodes, where the connections themselves were not just gravitational but quantum in origin. This entanglement-seeded network explains a key mystery: why dark matter forms halos around galaxies with a specific cuspy density profile, rather than just smearing out into a uniform haze. The initial correlations from entanglement gave it a head start, a pre-existing pattern upon which gravity could efficiently build. Then, much later, normal matter, the protons, neutrons, and electrons that make up stars, planets, and us, simply followed the lead of this dark architecture. As the universe continued to expand, the gravitational wells created by the clumped dark matter pulled in the visible gas, providing the foundation upon which the first galaxies could coalesce and shine. In this view, every brilliant spiral and elliptical galaxy we see is merely the visible tracer of an ancient, invisible, and quantumly woven framework. This theory offers an elegant solution to a persistent puzzle in cosmology known as the missing satellites problem. When scientists run sophisticated computer simulations of how dark matter should clump under the force of gravity alone, they predict that our own Milky Way galaxy should be surrounded by thousands of small dark matter halos, each massive enough to host a small dwarf galaxy. Yet, when we look at the sky, we only observe a few dozen of these satellite galaxies. It's a glaring discrepancy between theory and observation. The dark matter entanglement seed theory, however, can naturally resolve this. If dark matter particles were initially entangled, their quantum properties would have influenced how they clustered. The specific nature of that primordial entanglement could have suppressed the formation of the very smallest halos, preventing them from ever gathering enough gas to form visible stars. The entangled dark matter would have a kind of quantum pressure or a specific correlation length that made it less likely to fragment into the myriad tiny clumps that simulations predict. What we perceive as missing satellites aren't missing at all. They are simply dark, failed galaxies, their formation halted by the very quantum rules that govern dark matter at the dawn of time. The quest to verify this idea pushes the boundaries of modern astrophysics. While we cannot directly see this ancient entanglement, we can look for its cosmic fingerprints. One promising method involves meticulously mapping the large-scale structure of the universe with unprecedented precision. Projects like the Dark Energy Survey and the future Euclid Space Telescope are creating three-dimensional charts of billions of galaxies. By studying the subtle statistical correlations in how these galaxies are distributed, the way they cluster together on vast scales, scientists can infer the properties of the underlying dark matter web. If the dark matter was born from an entangled state, it should leave a specific, non-random signature in this cosmic web, a telltale pattern in the clustering that differs from models where dark matter has no such quantum history. Another frontier is the search for indirect signals from dark matter annihilation. If WIMP are the correct candidate, they might occasionally collide and annihilate each other, producing a faint drizzle of gamma rays. The pattern and intensity of this radiation across the sky could, in principle, reveal the underlying distribution of dark matter, and whether that distribution bears the hallmarks of an initial quantum-connected state. We are, in effect, learning to read the ghostly traces of a quantum conversation that ended nearly 14 billion years ago. One of the most profound puzzles in all of existence is simply this: why is there anything at all? More specifically, why is the universe made almost entirely of matter, when our most fundamental laws of physics suggest that the Big Bang should have created equal amounts of matter and its mirror opposite, antimatter? According to everything we know, for every particle of matter born, a particle of antimatter should have been created alongside it. When matter and antimatter meet, they annihilate each other in a burst of pure energy. If the cosmos had begun with a perfectly balanced ledger, all of its contents should have mutually destroyed one another, leaving behind a vast, empty expanse of radiation. The fact that we live in a cosmos brimming with galaxies, stars, and planets means that for some reason this perfect symmetry was broken. An almost imperceptible bias for matter over antimatter must have existed, and the question of what created that bias has stumped physicists for generations. Now, a fascinating theory suggests the answer lies in the universe's very first quantum entanglement, a primordial event that tipped the cosmic scales in our favor. This theory, known as leptogenesis in its more specific forms, proposes that the first stable entangled pairs in the infant universe were not just any particles, they were entangled matter-antimatter pairs. Picture the fiery dawn of creation, a seething plasma where particles and their antiparticles were constantly popping into and out of existence. Among this chaos, certain pairs of heavy, exotic particles, let's call them the X and anti-X particles, formed in a quantum embrace. These were unstable giants destined to decay into the lighter particles we know today, like quarks and electrons. The critical moment came during their decay, a process governed by the delicate rules of CP symmetry. CP stands for charge and parity, and this symmetry essentially means that the laws of physics should treat a particle and its mirror image antiparticle identically. If you filmed a particle interaction and then swapped every particle with its antipartner and viewed the film in a mirror, the physics should look exactly the same. Yet, in a stunning discovery, we have learned that this is not entirely true. There is a tiny, subtle CP violation in nature, a slight preference in how certain particles decay compared to their antimatter counterparts. Here is where quantum entanglement becomes the cosmic catalyst. The theory posits that this CP violation did not occur randomly. Instead, it was directly influenced by the entangled state of those primordial X and anti-X pairs. Because their fates were linked, the decay of one particle instantaneously affected its partner, even as they were flying apart. This non-local connection orchestrated their decay in a subtly biased way. Due to CP violation, the entangled decay pathways for the X particle might have favored producing just one more quark than antiquark, while the correlated decay of its anti-X partner might have been skewed to produce fewer antiquarks to balance the books. The net result across countless such entangled pairs was a microscopic but decisive excess of matter over antimatter. It was a universe-wide conspiracy enacted through quantum connections that left behind one extra matter particle for every billion annihilations. That one in a billion surplus is all it took. Everything we see in the universe today, every atom in your body, every star in the night sky, is the residue from that minuscule, entangled, imposed imbalance. This idea transforms our understanding of quantum mechanics from a curious microscopic phenomenon into the very author of cosmic destiny. Without that initial entanglement enabling a coordinated CP violation, the decay of the X and anti-X particles would have been independent and statistically even, perfectly cancelling each other out and leaving no surplus. The spooky action at a distance becomes the universe's founding act of creativity, the mechanism that broke a perfect symmetry and allowed for a material cosmos to exist. To appreciate how delicate this process was, consider an analogy with a vast cosmic coin-tossing competition. Imagine trillions of pairs of people, each pair sharing a single entangled coin. Normally, if you toss a fair coin, you get heads half the time and tails half the time. But in our cosmic contest, thanks to the entangled link and the rule of CP violation, whenever one person in a pair gets a matter result, their partner is subtly influenced to get a result that doesn't quite cancel it out. After all the tossing is done, for every billion pairs, you find you have one single leftover matter coin. That single coin, multiplied across the entire universe, represents all the galaxies we see today. The search for evidence to support this breathtaking idea drives some of the most advanced experiments in particle physics. Scientists at facilities like the Large Hadron Collider are desperately searching for new, heavy particles that could be the X and anti-X particles of this theory. They are meticulously studying the decay of known particles like B mesons to measure the precise details of CP violation, looking for effects that are too large to be explained by our current models. These discrepancies could be the direct fingerprints of new physics that once governed the early universe. Furthermore, researchers are investigating the behavior of neutrinos, ghostly particles that barely interact with matter. Neutrinos may hold a key, as they could be their own antiparticles, a property that would have profound implications for how they could have participated in those first entangled processes. By studying neutrino oscillations, how they change from one type to another, physicists are testing for additional sources of CP violation that could have fueled the matter-antimatter asymmetry. Every new datum collected is like finding another piece of a puzzle that was set in motion nearly 14 billion years ago, a puzzle whose solution seems inextricably linked to the universe's first quantum connections. We've journeyed through ideas where the first entanglement was a handshake across multiverses, an inheritance from a past cosmic cycle, and even a catalyst for the matter in our universe. But what if that first connection wasn't a singular, dramatic event at all? What if it was the outcome of a cosmic competition, a battle for survival in the chaotic arena of the early universe? This brings us to a truly fascinating perspective known as quantum Darwinism, applied to the Big Bang itself. This theory proposes that the universe's first stable quantum entanglement was the winner of a relentless process of environmental selection, the one configuration that was robust enough to copy itself, proliferate, and ultimately give rise to the familiar classical world we inhabit today. At its heart, quantum Darwinism is a framework designed to solve one of the deepest puzzles in physics. Why do we live in a world of definite objects while the quantum realm beneath is a fuzzy cloud of probabilities? In the strange world of quantum mechanics, a particle can exist in a superposition, meaning it can be in multiple states or places at once until it is measured. Yet, when we look at a chair, it is definitively here, not in a superposition of being both here and over there. The standard explanation is that when a quantum system interacts with its environment, for instance, when a particle is buffeted by photons and air molecules, it undergoes a process called decoherence, which effectively destroys its quantum coherence and makes it behave classically. Quantum Darwinism takes this a crucial step further. It suggests that among all the possible quantum states, only a select few are fit enough to be widely replicated and disseminated into the environment. These special states are called pointer states, and they are the ones we consistently measure and agree upon. The environment acts like a witness, making countless copies of these robust states, and our perception of a single, objective reality emerges from this consensus. Now let's scale this idea up to the ultimate beginning. Imagine the universe in its first moment, a seething, chaotic quantum foam where every possible configuration of spacetime and energy flickered in and out of existence. It was a realm of pure potential, a superposition of countless possible universes, each with its own set of physical laws. In this primordial chaos, countless fleeting entanglements formed and broke apart. Most were too fragile, instantly destroyed by the violent fluctuations around them. But according to this theory, one particular entangled state, or a small set of them, possessed a unique property: exceptional stability. This state was resilient. It could interact with the raging environment of the quantum foam without completely disintegrating. Its information could be copied and imprinted onto the surrounding fabric of reality. This robust entangled state was naturally selected. It was the one that could proliferate, its correlations spreading and multiplying as the universe expanded, effectively recruiting more and more of the quantum foam into its stable, correlated network. This process of quantum natural selection provides a powerful and elegant mechanism for the transition from the quantum to the classical world. The moment that robust entanglement began to be widely copied throughout the nascent cosmos was the moment our classical universe was born. The pointer states that were selected defined the very rules of the game. They dictated which observables would become the fixed properties of our reality, things like position and momentum, which we now take for granted as classical certainties. In this view, the laws of physics we hold as fundamental are not written on a cosmic stone tablet. They are the emergent classical shadows of that first winning quantum configuration. They are the rules that proved most effective at surviving and replicating in the specific environmental conditions of our early universe. The fact that we observe a universe with 3 spatial dimensions, a specific strength of gravity, and a constant speed of light might simply be because the entangled state that gave rise to these properties was the most fit to survive and dominate. Let's make this abstract idea more concrete with an analogy from biology. Think of the early quantum foam as a vast primordial soup, much like the conditions on early Earth. Within this soup, many different molecular structures form randomly. Most are unstable and fall apart immediately, but one particular molecular structure, perhaps a primitive form of DNA or RNA, has a unique property: it can make copies of itself. This self-replicator doesn't need to be the most complex molecule, just the one that is stable enough to withstand the chaotic environment and accurate enough in its replication to outcompete others. That molecule becomes the ancestor of all life on Earth. In the quantum Darwinism Big Bang, the first stable entanglement is that cosmic self-replicator. It wasn't the only possible beginning, but it was the one that could best replicate its information structure across the expanding universe, eventually leading to the consistent classical reality we now explore. This framework offers a profound new way to think about the fine-tuning of the universe. Instead of asking why the laws of physics seem perfectly tuned for complexity and life, we can now ask, what made this particular set of laws so stable and prolific? The constants of nature may have the values they do because those values are an attractor in the landscape of all possible quantum states, a stable fixed point that naturally emerges from the process of environmental selection. It suggests that if we could somehow peer into the multiverse, we might find that universes with laws like ours are not astronomically rare, but are in fact common because they represent the stable, self-replicating outcomes of quantum cosmological evolution. Our existence isn't a miracle in an otherwise hostile cosmos. It is a testament to the stability and durability of the quantum architecture that won the competition at the dawn of time, an architecture whose first successful thread was a uniquely robust quantum entanglement. Yet, as we've seen, the early universe was a place of profound symmetry. But what if that symmetry was even greater than we've so far imagined, encompassing a perfect partnership between the 2 fundamental classes of particles? This brings us to a theory that posits a truly elegant origin for the cosmic rulebook, the supersymmetry breaking trigger. To understand this, you first need to grasp the core idea of supersymmetry, often nicknamed SUSY. It's a beautiful, mathematically compelling concept that proposes a deep, underlying kinship in nature. For every known particle in the Standard Model, every electron, every quark, every photon, there exists a mysterious, hidden superpartner. These aren't just different particles, they are mirror images that transcend the classic divide. The particles that make up matter, like electrons, are called fermions. The particles that carry forces, like photons, are called bosons. Supersymmetry beautifully bridges this gap, suggesting that every matter fermion has a force-carrying boson for a superpartner, and every force boson has a matter fermion for its twin. In this perfect, symmetrical world, an electron, a fermion, would be partnered with a selectron, a boson. A photon, a boson, would be partnered with a photino, a fermion. Now imagine the universe in its very first instance, a realm of almost inconceivable energy where this supersymmetry wasn't just a theory but a living, breathing reality. Particles and their superpartners coexisted in a state of perfect balance, possessing identical masses and intimately connected natures. It is within this pristine, high-energy symphony that our theory places the universe's first quantum entanglement. But this wasn't a connection between two random particles. The hypothesis suggests that the very first stable, enduring quantum link was forged between a particle and its own superpartner. Picture an electron and its selectron, born from the fire of creation, instantly and irrevocably entangled. Their fates were linked in the most fundamental way possible. This wasn't merely a partnership, it was a cosmic identity sharing a single quantum state, a connection so profound that it would ultimately orchestrate its own dissolution. This primordial entanglement between a particle and its superpartner acted as the trigger for a cosmic revolution, the breaking of supersymmetry. Think of it like a perfectly balanced seesaw with two identical weights. It's in a state of perfect symmetry. Now, if you were to instantly entangle the two sides so that the position of one dictates the position of the other, and then you introduce a tiny, random fluctuation, the entire system is forced to choose a new, stable state. The perfect balance is broken. In an analogous way, the act of entanglement between the particle and its superpartner in that volatile early environment introduced an instability into the perfect symmetry of the universe. The system could no longer sustain its perfect, high-energy form. As the universe expanded and cooled, this entangled state forced a dramatic transition. The superpartners, which once had the same negligible mass as their ordinary counterparts, suddenly acquired immensely heavy masses. In a cosmic instant, they were transformed from accessible partners into incredibly elusive, massive entities, effectively disappearing from the low-energy world that was rapidly emerging. The entanglement was the catalyst. It was the finger that tipped the first domino, leading to the shattering of a perfect symmetry and creating the asymmetric universe we inhabit today. The consequences of this event are absolutely central to our existence. The scale at which supersymmetry broke, determined by the specific nature of that first entanglement, directly set the mass for the Higgs boson. The Higgs field is what gives other fundamental particles their mass, and its own properties are deeply intertwined with supersymmetry. Without SUSY, the Higgs mass should be driven to unimaginably high values by quantum corrections, a problem known as the hierarchy problem. Supersymmetry's elegant cancellation of these corrections is its greatest appeal. Therefore, the energy at which the particle superpartner entanglement triggered the break set the mass of the Higgs, which in turn dictated the masses of the W and Z bosons that carry the weak nuclear force. This single quantum event didn't just hide a set of particles, it determined the very strength of one of the four fundamental forces and set the mass scale for all the ordinary matter that would later form stars, planets, and us. The fact that the weak force is weak enough and the Higgs boson is light enough for complex structures to form might be a direct legacy of that first, fleeting quantum handshake between a particle and its shadow. The search for evidence of this theory drives some of the most ambitious experiments in human history, primarily at the Large Hadron Collider. Physicists are desperately searching for any sign of these superpartners. If supersymmetry is a true symmetry of nature, and it was broken at the scale this theory suggests, then the LHC should have enough energy to produce at least the lightest of these superpartners. Finding one would be a monumental discovery, not just confirming a beautiful theory but potentially validating this entire narrative of an entanglement-driven cosmic transition. Beyond colliders, scientists also look for indirect effects. The specific properties of the Higgs boson, now that we've discovered it, offer clues. Its measured mass and interactions are tantalizingly consistent with low-energy supersymmetry, acting as a ghostly echo of that high-energy broken symmetry. Furthermore, the lightest superpartner, often thought to be a neutralino, is a prime candidate for the dark matter that permeates our galaxy. This would create a breathtakingly unified picture, the same quantum event that gave particles their mass and hid a world of superpartners also, in one fell swoop, produced the invisible cosmic scaffolding that guides the formation of galaxies. The universe's first entanglement, in this view, becomes the master key that locked in the fundamental parameters of our reality, from the forces that govern atomic nuclei to the dark matter halos that bind the cosmos together. But to truly appreciate the pivotal role of that first quantum handshake, we must shrink our perspective even further, down to the very smallest conceivable scales, where the idea of a point-like particle dissolves into something far more elegant. This leads us into the intricate and mesmerizing domain of string theory, and a specific proposal we might call the first vibrations of the string theory landscape. At its heart, string theory makes a breathtaking leap. It suggests that the fundamental building blocks of the universe are not zero-dimensional dots, but unimaginably tiny, one-dimensional loops or strands of energy vibrating strings. And just as a single violin string can produce a vast range of notes depending on how it vibrates, the distinct vibrational patterns of these cosmic strings give rise to every particle and force we see. An electron is a string vibrating one way. A quark is that same string vibrating another way. A photon carrying light is yet another resonant frequency. In this framework, all the rich diversity of the cosmos emerges from the symphony of these microscopic strings. Now, where does the landscape come in? The mathematics of string theory doesn't point to one single, unique universe. Instead, it suggests a staggering plurality of possibilities, a vast, perhaps infinite, landscape of potential vacuum states. Think of this landscape not as a physical place, but as a cosmic menu of all possible realities, each with its own unique set of physical laws and constants. One entry on this menu might describe a universe where gravity is 1 billion times stronger, causing it to collapse instantly. Another might describe a universe with 10 spatial dimensions, all but 3 of them curled up into invisibility. Our universe, with its specific strength of gravity, mass of the electron, and value for the speed of light, is just one particular point in this inconceivably vast landscape. The monumental question, then, is how did our cosmos end up with this specific, life-permitting recipe from the menu? This is where the first quantum entanglement makes its grand entrance, not between particles, but between the strings themselves. The theory posits that in the roiling quantum foam of the very early universe, countless strings were vibrating in a chaotic superposition of all possible states. They were, in a sense, trying out every possible note on the cosmic menu at once. Amidst this cacophony, a specific set of strings, through their interactions and proximity, became quantumly entangled. Their vibrational states became inextricably linked. This was not a random event, but a specific correlation that selected for a particular combination of vibrational patterns. And this specific combination of entangled vibrations corresponded directly to one particular vacuum state in the string theory landscape, ours. The act of entanglement was the cosmic act of measurement. It collapsed the infinite possibilities down to one definite reality, stabilizing our particular vacuum and locking in the physical constants that define our existence. The first entanglement was the moment the universe chose its tune from the symphony of possibilities. To grasp the profound stability this provides, consider a metaphor. Imagine a vast field of hills and valleys representing the string theory landscape. Each valley is a stable vacuum state where a universe could reside. Our universe is sitting in one particular valley. Now, what keeps it there? Why doesn't it just randomly tunnel or jump to another valley with different physical laws? The answer proposed by this theory is the web of quantum entanglement. The initial entanglement between those foundational strings created a deeply correlated network. This network acts like a powerful anchoring system, a kind of quantum glue that holds our vacuum state in place. It resists decoherence and protects the delicate vibrational patterns that define our laws of physics from being disrupted by quantum fluctuations. Without this persistent entanglement, the constants of nature might drift, or our universe might make a catastrophic leap into a different vacuum. a transition that would instantly and utterly annihilate all structure as we know it. The enduring, spooky connections forged at the dawn of time are what provide the consistent, reliable backdrop against which galaxies can form, stars can burn, and life can evolve. This idea offers a breathtakingly unified explanation for the fine-tuning of the cosmos. The reason our universe has such precise constants isn't because it won a cosmic lottery, but because the specific entangled state that crystallized our vacuum was uniquely robust and self-reinforcing. It was a configuration that promoted further entanglement and complexity. The vibrational patterns that gave us electromagnetism and the strong nuclear force were those that could form stable, long-range correlations. This perspective turns the fine-tuning problem on its head. We don't live in a randomly selected, fine-tuned universe. We live in a universe whose laws are the way they are because those are the laws that are stable and reproducible through the mechanism of quantum entanglement. The universe isn't fine-tuned for life. Life is a complex consequence of a universe whose laws are stable enough to allow for its emergence, and that stability is a direct gift from the first quantum connections between the vibrating strings of reality. The implications ripple out to the very largest scales. The dark energy that is causing the accelerated expansion of our universe, for instance, is simply the energy inherent in our specific vacuum state, the energy of our particular valley in the landscape. Its value is what it is because of the vibrational patterns locked in by that primordial entanglement. Furthermore, this framework provides a new way to think about the beginning of cosmic inflation. The rapid, exponential expansion of space may have been triggered the moment our vacuum was selected and stabilized by that initial string entanglement. It was the process of the universe settling into its chosen state, with inflation smoothing out the wrinkles and imprinting the correlations of that first entanglement across the entire sky, ultimately manifesting as the temperature variations we see in the cosmic microwave background. In this view, the entire history of our cosmos, from its first moment to its ultimate fate, is an unfolding story written in the language of vibrating strings, a story whose first coherent sentence was a quantum entanglement that defined everything to come. But what if the very fabric of space and time is not a smooth, continuous sheet, but is instead constructed from a vast collection of discrete, individual moments? This is the radical proposition of causal set theory, a compelling approach to quantum gravity that offers a startlingly simple answer to the question of the first quantum entanglement. In this framework, the universe is not made of a fabric but of a vast set of fundamental events. Think of them as the indivisible atoms of spacetime. These events are not scattered randomly, they are partially ordered by a single, fundamental relationship, which event can influence another. One event either comes before another or it does not. There is no concept of distance or duration at this most basic level, only this raw, binary connection of causality. And within this starkly elegant vision, the universe's very first quantum entanglement is theorized to have been the spontaneous formation of the first causal link. The moment a second spacetime atom emerged from the primordial void and established a before and an after with the very first one. This was not a connection in space and time, but the act that created the possibility of sequence and history itself. To grasp how profound this shift in perspective is, consider the difference between a smooth, flowing river and a sequence of individual frames in a movie. Our everyday experience tells us that spacetime is like the river, a continuous, flowing medium. But causal set theory suggests that this is an illusion, much like the smooth motion we perceive in a film is an emergent property of 24 static frames flashing by every second. At the Planck scale, reality is a vast collection of discrete frames or events. The only thing that gives these events meaning is their order. If one event can send a signal to another, then a causal link exists between them. The entire cosmic history from the Big Bang to this very moment is then nothing more than an immense branching network of these causal links. The first quantum entanglement in this view was the crystallization of the very first such link. It was the universe's inaugural if-then statement, a fundamental decree that something could now come after something else, setting in motion the irreversible flow of causality that would eventually build everything we know. This initial link did not exist in isolation. Its creation immediately opened the door for a dramatic cascade. Think of it like the first falling domino in an unimaginably vast and complex chain. The existence of that first connected pair of events created a new context, a new now from which further events could spring. According to the theory, this process is driven by a kind of cosmic logic called transitive closure. If event A is linked to event B and event B is linked to a new event C, then A is automatically linked to C as well. Each new event that is born only needs a minimal number of direct links to its immediate predecessors, but through transitivity, it becomes woven into the entire growing web of causality. The first entanglement was the spark that ignited this chain reaction, a process of prolific link generation that rapidly built up the entire causal structure of the universe. The breathtaking four-dimensional spacetime of general relativity, with its curved geometry and cosmic history, is then seen as a secondary, emergent approximation of this deeper, more fundamental network of discrete connections. This bottom-up relational approach turns our conventional understanding of physics completely on its head. In most models, spacetime is the primary stage, and particles and fields are the actors upon it. But in causal set theory, the stage itself is built from the relationships between the actors. There is no space without connection. There is no time without sequence. The properties we associate with space, like distance and volume, are not fundamental. They emerge from the collective pattern of the causal links. A large volume of space in this model corresponds to a region of the causal set with a very high density of events and links. The force of gravity itself and the curvature of spacetime in Einstein's theory are understood as manifestations of the underlying statistics of this causal network. A region we would perceive as having strong gravity is simply a region where the pattern of links is such that events are more highly interconnected in a specific way. This means that the universe's first quantum entanglement, by establishing that first causal link, didn't just create a sequence, it planted the seed for the entire geometric structure of reality, including the force that holds planets in their orbits. Now, let's journey into one of the most philosophically daring interpretations of quantum mechanics, a perspective that turns our conventional understanding of cause and effect inside out. This is the transactional interpretation, and within its framework, the universe's first quantum entanglement is reimagined as a cosmic handshake across time itself. Developed by physicist John Cramer, this interpretation resolves the infamous measurement problem, the puzzle of why a particle exists in multiple potential states until we observe it, at which point it seems to randomly choose one definite reality. The standard explanation, the Copenhagen interpretation, simply accepts this random collapse as a fundamental, inexplicable axiom. The transactional interpretation, however, offers a breathtakingly elegant mechanism. It proposes that every quantum event is a negotiation, a deal struck between the past and the future. It involves two kinds of waves, the familiar retarded waves that travel forward in time from a source, and their hidden partners, advanced waves that travel backward in time from a future absorber. The moment of measurement of definite reality occurs when these waves meet and form a closed loop, a self-reinstating handshake that transfers energy and solidifies a single outcome from the fog of possibilities. The implications for the origin of the cosmos are staggering. In this model, the very first quantum entanglement in the universe wasn't just a link between two particles in space. It was the inaugural transaction, the first successful handshake between the nascent past and the waiting future of the entire cosmos. Picture the universe at time zero, a seething superposition of every possible initial state. From this chaotic beginning, retarded waves of possibility fanned out into the future. But from the far future, from the ultimate fate of the universe where all the potential outcomes would need to be absorbed, advanced waves traveled backward in time. The first stable entanglement was the moment a specific advanced wave from the future found a matching retarded wave from the past, and they resonated, locking into a self-consistent loop. This transaction didn't just create a pair of entangled particles. It selected the entire initial wave function of the universe, defining the specific reality we now inhabit from an infinite set of parallel possibilities. Our entire cosmic history, in this view, was crystallized by a handshake that reached across 14 billion years. This interpretation is profoundly time-symmetric, treating the past and the future with equal footing. We are accustomed to thinking of time as a one-way street where the past causes the future, but the transactional interpretation suggests this is an illusion born from our limited perspective. At the most fundamental level, the future is just as involved in shaping the present as the past is. The advanced waves traveling backward in time are not mere mathematical curiosities, they are physically real components of the quantum world. This provides a stunningly intuitive mechanism for the infamous, spooky action at a distance in quantum entanglement. When we measure one particle of an entangled pair, its wave function collapses to a definite state. Instantly, its partner, no matter how far away, does the same. How, in the transactional picture, the measurement is the offer wave. The confirmation, the handshake that completes the transaction, is an advanced wave that travels back in time to the moment of entanglement, ensuring both particles are correlated in a way that is consistent with the final measurement. The connection isn't spooky, it's a closed time-like loop, a pre-arranged deal written into the very fabric of reality. Applying this to the cosmic scale offers a radical new solution to the problem of wave function collapse. The question of what collapses the universal wave function has long plagued cosmology. If everything is quantum, who or what is the external observer for the entire universe? The transactional interpretation bypasses this entirely. The cosmos doesn't need an outside observer. It observes itself through time. The first transaction was a self-measurement, a loop closed between the Big Bang and the ultimate future. The specific configuration of our universe, its physical constants, the pattern of galaxies, the existence of life, is not a random accident. It is the one consistent solution that satisfied the handshake conditions between its beginning and its end. This idea resonates powerfully with the concepts of convergent or teleological causation in physics, suggesting that the final state of the cosmos plays an active role in selecting its initial conditions. We live in this particular universe because it is the only one where the offer from the beginning and the confirmation from the end could perfectly agree, creating a stable, self-consistent timeline from start to finish. To visualize this abstract concept, think of a novelist plotting a complex mystery. The author knows the ending, the final reveal of the murderer. As they write the first chapter, they plant clues and develop characters in a way that is perfectly consistent with that predetermined conclusion. The beginning and the end are inextricably linked, each defines the other. In the transactional interpretation, the universe is that novel. The Big Bang is the opening sentence, and the final state of the cosmos is the last page. The first quantum entanglement was the moment the author solidified the core plot twist, a decision that echoed both forward and backward through the narrative, ensuring every subsequent event would weave together into a single, coherent story. We, living somewhere in the middle chapters, experience time linearly, but the underlying structure of reality is a complete, self-consistent whole, with the future quietly guiding the past just as much as the past creates the future. This transforms our understanding of reality from a chain of cause and effect into a single, timeless tapestry, where the first quantum handshake was the master stitch that set the entire pattern in motion. Another ghostly presence permeates the cosmos, one even more elusive than dark matter, and it may have been the universe's most prolific matchmaker. We are surrounded by a vast cosmic ocean of neutrinos, often called ghost particles, that barely interact with matter at all. Trillions of them pass through your body every second, leaving no trace, as if you were transparent. This isn't just a curious fact, it's a relic of the Big Bang itself. In the first second of creation, the universe was so hot and dense that neutrinos were constantly colliding and interacting, trapped in the thick primordial soup. But as the cosmos expanded and cooled, roughly 1 second after the beginning, a pivotal event occurred known as neutrino decoupling. Suddenly, the density dropped enough that these ghosts could fly freely, no longer impeded by the rest of matter. This created a background sea of relic neutrinos, a fossil field that has been flowing through the universe ever since, and it is within this sea that our next theory finds its origin. The sheer properties of these neutrinos made them the ideal candidates for the universe's first large-scale quantum entanglement. Their most defining trait is their profound weakness. Unlike electrons or quarks, neutrinos are immune to the electromagnetic force and the strong nuclear force. They interact only via the weak nuclear force and gravity, and even then, only rarely. This feebleness is their superpower in the quantum realm. In the chaotic early universe, most particles were constantly bombarded, their delicate quantum states shattered by countless collisions in a process called decoherence. But neutrinos, having decoupled so early, were largely left alone. Their weak interactions meant that once a pair of them became entangled, that connection was far less likely to be disrupted by the environmental noise. They could maintain their quantum coherence over vast distances and for astonishing lengths of time, acting as stable, long-range connectors in the infant cosmos. This theory posits that in the moments just before and during their decoupling, a significant portion of this relic neutrino sea became quantumly entangled. It wasn't just a few pairs here and there, it was a vast, interconnected network, a web of quantum links woven through the entire universe. Because neutrinos were so incredibly abundant, outnumbering protons and electrons by billions to one, this entanglement network would have been the most extensive quantum system in existence. Its scale would have been truly cosmic. As the universe continued to expand, these entangled neutrinos were pulled apart, their connections stretching across the growing expanse of space. Yet, thanks to their ghostly nature, those links remained intact, creating a fossilized imprint of the universe's first large-scale quantum state, a subtle pattern of correlation frozen into the fabric of reality. This pervasive neutrino entanglement background could have left a detectable signature on the oldest light we can observe, the cosmic microwave background. The CMB is the afterglow of the Big Bang, released when the universe became transparent to light about 380,000 years after its birth. But remember, neutrinos decoupled over 379,000 years earlier. For all that time, this web of entangled neutrinos was already permeating the cosmos. Their presence and their correlated quantum states would have exerted a subtle gravitational influence on the primordial plasma. The density fluctuations that eventually created the hot and cold spots in the CMB were not formed in a vacuum. They evolved in a universe already laced with this neutrino entanglement network. The specific statistical patterns we see in the CMB's temperature variations, the way the hotspots correlate with each other across the sky, might carry the faint fingerprint of this ghostly quantum web, a signature that cosmologists are now searching for in ever more precise data from telescopes like Planck. Furthermore, this ancient entanglement could be actively influencing particle physics phenomena we observe today, specifically in the bizarre behavior of neutrino oscillations. We've discovered that neutrinos are not static. They have a chameleon-like nature, morphing between three different types: electron, muon, and tau neutrinos as they travel through space. This oscillation is a purely quantum mechanical phenomenon. The prevailing theory suggests that a neutrino is born as a specific mixture or superposition of all three mass states, and this superposition evolves over time. Now, imagine if a relic neutrino from the Big Bang, part of that primordial entangled sea, were to interact with a modern neutrino from the Sun or a particle accelerator. Their interaction could be profoundly affected by that ancient quantum link. The oscillation pattern of the contemporary neutrino could be subtly shifted or correlated with the state of its primordial partner, even if that partner is on the other side of the galaxy. While this effect would be incredibly subtle and difficult to detect, it suggests that the ghostly hand of the first universe is still subtly guiding the behavior of particles today. The implications of this are as profound as they are strange. It means that the universe is not just filled with a sea of ancient particles, it is filled with a sea of ancient connections. Every cubic centimeter of space is likely suffused with these relic entangled neutrinos, a living fossil of the universe's quantum infancy. This provides a tangible, physical substrate for the kind of pervasive interconnectedness that other theories, like the holographic principle, describe in more abstract terms. The neutrino sea is the closest thing we have to a direct particle-based memory of the universe's first second. Studying it is not just about understanding a type of particle, it's about decoding the original quantum architecture of everything. The hunt for these relic neutrinos is one of the most formidable challenges in experimental physics, as their energy is so low that they are nearly impossible to detect with current technology. Yet the potential reward is unparalleled, direct evidence of the universe's first and most enduring quantum relationships, written in the ghostly script of the cosmos's most elusive particles. Yet another theory invites us to imagine the universe not as a stage, but as a network, a living, evolving web of relationships. This is the quantum gravity model, and it proposes a concept so radical that it challenges the very idea of what space is. In this framework, space is not a fundamental, pre-existing container. It doesn't come first with particles and fields placed inside it. Instead, space is an illusion, a collective phenomenon that emerges from something far more basic, a vast, dynamic network of quantum bits or qubits. Think of it like a social network. Each person is a node, and their friendships are the links. The space of that society isn't defined by physical addresses, but by the pattern of who is connected to whom. In quantum gravity, the entire cosmos is such a network. Each point or node is a fundamental quantum system, and the links between them represent potential interactions. The universe's first quantum entanglement, therefore, was not an event in this network. It was the event that gave the network its initial defining structure. To grasp how this emergence works, we need to rewind to the universe's absolute beginning. According to this model, the cosmos started in a state of perfect connectivity. It was a high-energy, frantic chaos where every single quantum bit was directly linked to every other bit. Picture a dense, blindingly bright jewel where no point is any farther from another than a single connection. In this state, the concept of distance was meaningless because everything was a neighbor to everything else. There was no space as we know it, just a seething, amorphous blaze of pure connection. This was a state of maximum information and maximum energy, but it was also featureless and without any geometry or direction. It was the ultimate symmetry, but a symmetry so perfect that it couldn't support the complex structures we see today. The universe was a single, undifferentiated whole, a cosmic everything at once. The pivotal moment in cosmic history, according to quantum gravity, was not an explosion but a cooling, a cosmic freezing. As the universe expanded and its energy density dropped, it underwent a phase transition, much like water freezing into ice. In this process, the network could no longer sustain the energy cost of maintaining every single possible link. Connections began to break. Think of it like a vast cosmic light show where every bulb is initially connected to every other bulb by a bright wire. As the power drops, wires start to snap at random. But they don't all break. A specific, stable pattern of connections survives the freezing process, and the very first persistent quantum entanglement in this model was the survival of one such specific pattern. It was the first set of links that proved stable enough to resist decoherence and remain correlated as the universe cooled. This surviving web of entanglement didn't just exist within space, it was the nascent structure of space itself. This is where the magic of emergence truly takes hold. The specific pattern of surviving connections in this network directly determined the dimensionality and geometry of the space we now inhabit. Why do we experience three spatial dimensions? It's not a fundamental law written in the stars. In the quantum gravity model, it's because the particular graph that froze out the specific arrangement of which nodes stayed connected to which others happens to have the mathematical properties that, on a large scale, look and behave exactly like a three-dimensional grid. It's analogous to looking at a tightly packed honeycomb. Up close, you see the individual wax cells and their connections, but from a distance, it appears as a smooth, continuous sheet. In the same way, the microscopic, graph-like structure of the underlying quantum network gives rise to the smooth, continuous space we move through every day. The reason you can move forward, backward, up, down, left, and right is a direct consequence of the connectivity pattern that crystallized in that first moment. This model provides a breathtakingly elegant explanation for one of the most sacred principles in physics, the constant speed of light. In Einstein's special relativity, the speed of light is a universal constant, and the laws of physics are the same for all observers, a principle known as Lorentz invariance. But in quantum gravity, this is not a fundamental rule. It is a low-energy approximation, an emergent property of the underlying graph structure. Imagine information trying to travel across this network. It can't jump from any node to any other. It has to hop along the surviving links. The maximum speed at which information can propagate through this graph from one node to its neighbor, then to the next, defines what we perceive as the speed of causality, the speed of light. If the graph were differently connected, information might travel faster or slower, or even in anisotropic ways, meaning light would travel at different speeds in different directions. The fact that we observe a perfectly constant speed of light in a vacuum suggests that the graph underlying our reality is exceptionally uniform and regular on large scales, a frozen relic of that first stable entanglement pattern. The implications of this are as profound as they are strange. It suggests that if we could ever probe physics at incredibly high energies near the Planck scale, we might witness the granular, graph-like nature of spacetime. Lorentz invariance might break down, and we might see slight deviations from Einstein's perfect laws. The speed of light might not be a constant but could have varied in the very early universe when the network was still settling into its current configuration. This offers potential solutions to several cosmic puzzles, such as the horizon problem, without needing a period of inflation. If the universe's connectivity was different at the beginning, allowing for faster-than-light information transfer in the dense network, then distant regions could have been in causal contact after all. We are, in effect, living in the low-energy, frozen phase of a cosmic graph, and the first quantum entanglement was the event that selected the specific geometric and physical rules of our particular icy reality. Now we journey to one of the most elegant and visually captivating theories of all, a concept that paints the Big Bang not as a mysterious singularity, but as one side of a cosmic balance sheet. This is the black hole-white hole entanglement, a theory that dares to suggest our entire universe is the radiant, expansive output of a white hole, born from a quantum connection to a black hole in a separate realm of reality. To grasp this, we first need to understand its two key players. We're all familiar with black holes' cosmic traps from which not even light can escape, regions where matter and energy are crushed into an infinitesimal point, a singularity. But what about their theoretical opposite? A white hole is a hypothetical region of spacetime that nothing can enter. It can only expel matter and energy outward. It's like a black hole running in reverse, a cosmic fountain of infinite energy, perpetually spewing out its contents. While we have never observed a white hole in our universe, the equations of general relativity allow for their existence, and this theory places them at the very center of the cosmic origin story. The proposal is as beautiful as it is profound. The universe's first quantum entanglement wasn't between two particles, but between two entire spacetime geometries, a primordial black hole in one realm and a white hole in another. These two objects, forever linked by their quantum states, formed a stable structure known as an Einstein-Rosen bridge, which we commonly call a wormhole. In this breathtaking picture, the black hole side represents the ultimate gravitational collapse of a pre-existing state, perhaps a dying universe in another cosmic cycle or a region of a larger multiverse. All the matter and energy that fell into that black hole was funneled through the wormhole, not to be destroyed in a singularity, but to be transmitted through the entanglement channel. And on the other side of that bridge, that immense influx of energy and information burst forth as the Big Bang itself, the explosive beginning of our own cosmos. Our universe, in this view, is the white hole. This provides an incredibly elegant solution to several thorny problems in cosmology. First, it addresses the troubling nature of the initial singularity. The standard Big Bang model begins with a point of infinite density and temperature, where the laws of physics as we know them break down completely. It's an unsatisfying starting point for science. The black hole-white hole model offers a non-singular beginning. The information and energy that formed our universe didn't originate from a mysterious, lawless point, but from the well-defined, albeit extreme, process of gravitational collapse in a neighboring region of reality. The Big Bang was simply the other end of that process, the moment the entangled white hole began its active phase of expulsion. This also naturally explains the universe's immense initial energy. It was simply the total mass energy of whatever colossal structure collapsed to form the parent black hole, transferred to us through the cosmic pipeline of the wormhole. This theory also beautifully aligns with the ER equals EPR conjecture we explored earlier, which links entanglement to wormholes. Here, that idea is scaled up to its ultimate conclusion. The quantum entanglement between the black hole and white hole is the wormhole connecting them. This provides a perfect mechanism for preserving information, resolving the black hole information paradox on a cosmic scale. All the information that falls into the parent black hole is not lost. It is faithfully transmitted through the entanglement channel and emerges to form the complex tapestry of our universe. The specific quantum states of the particles in our cosmos are direct reflections of the states of the particles that fell into the black hole eons ago. We are, in a very literal sense, the decoded information from another reality, a cosmic message that was received and manifested as our own existence. To visualize this, imagine a majestic cosmic tree. The roots of the tree, delving into the dark soil, represent the black hole, drawing in material and sustenance. The trunk is the wormhole, the entangled connection that acts as a conduit, and the glorious, branching canopy, bursting with leaves and reaching for the sky, is the white hole, our expanding, flourishing universe. One cannot exist without the other. They are two parts of a single, living system. This perspective completely reframes our place in the cosmos. We are not the isolated aftermath of a random explosion. We are part of a vast, cyclical, or perhaps branching cosmic ecology, where the death of one reality can give birth to another through the fundamental mechanism of quantum entanglement. The first connection was therefore the moment this circuit was completed, linking the end of one story to the beginning of ours in an eternal, self-consistent loop. Now, let's shift our perspective from networks and wormholes to consider the cosmic consequences of a broken symmetry, a process that might have literally tied the first knots in the fabric of reality. This is the theory of topological defect entanglement, which takes us back to the seething, cooling plasma of the very early universe. As the cosmos expanded from its unimaginably hot birth, it didn't cool smoothly and uniformly. Instead, it underwent a series of dramatic phase transitions, much like steam condensing into water or water freezing into ice. During these transitions, the fundamental quantum fields that permeate all of reality shifted to new, more stable states. But here's the catch: this shift couldn't happen in perfect coordination across the entire universe. Different regions, separated by distances too vast for light to have connected them, would have chosen their new vacuum states independently. Where these differing domains met, they couldn't always merge seamlessly. The result was the formation of stable, persistent flaws in the structure of spacetime itself, cosmic fossils known as topological defects. These defects come in several forms, each more exotic than the last. Imagine a vast cosmic honeycomb forming as the universe cools. If the rules of the transition are right, you might get one-dimensional flaws like cracks or scars known as cosmic strings. These are not strings of atoms, but unimaginably dense, incredibly thin filaments of pure energy, thinner than a proton but with the mass of a mountain range per inch, stretching across the entire cosmos. In other scenarios, two-dimensional sheets or domain walls could form, acting like vast, impenetrable membranes dividing regions of space with different physical properties. And in the most extreme case, point-like defects called magnetic monopoles could arise, theoretical particles that are just a north magnetic pole without a south, or vice versa, solitary magnets of cosmic power. According to this theory, the universe's first stable, large-scale quantum entanglement wasn't between random particles, but was intrinsically tied to the very birth of these bizarre cosmic structures. The mechanism is as elegant as it is powerful. The quantum fields that define these topological defects didn't just exist in isolation. As they crystallized out of the cooling universe, their configurations became quantumly entangled with the fields defining other, distant defects of the same type. Think of it like a vast, cosmic ice sheet cracking as it freezes. The pattern of cracks isn't random. The stress that causes one crack in one location is correlated with the stress causing another crack far away, even if they haven't directly communicated. In the quantum realm, this correlation is an actual, physical connection. A cosmic string forming on one side of the universe could have its fundamental quantum state, its vibrational mode, its energy instantly and permanently linked to a string forming on the opposite side. These defects didn't just become entangled, they were born entangled, acting as the first permanent, massive nodes in a primordial quantum network that was woven directly into the geometry of spacetime. This web of entangled defects could have provided the very blueprint for the cosmic structures we see today. Long before dark matter began to clump under gravity, this network of cosmic strings and other defects would have been the most prominent feature in the universe. Their immense mass would have exerted a powerful gravitational pull, and because they were entangled, their influence was coordinated. Matter would have begun to flow and cluster along the lines of this invisible, quantumly connected scaffolding. The great walls and filaments of the cosmic web, the vast chains of galaxies we observe with our telescopes, could be the direct descendants of this initial architecture. The entangled defects seeded the first over densities, the gravitational wells where gas could pool and eventually ignite into the first stars, guiding the construction of the universe in a way that pure random fluctuation couldn't achieve. They provided a head start, a pre-written pattern for gravity to follow. This theory also offers a compelling explanation for some of the most puzzling anomalies observed in the cosmic microwave background. The CMB is remarkably uniform, but it's not perfectly so, and some of the irregularities don't quite match the predictions of the standard inflationary model. Certain large-scale features, like the mysterious cold spot, a vast, unusually cold region in the southern sky, have defied easy explanation. Could this be the imprint of an ancient topological defect? A vast, entangled domain wall, for instance, casting a specific kind of shadow on the microwave background, or perhaps the distinctive patterns of lensing or polarization in the CMB could bear the signature of a network of cosmic strings whose entangled nature would create a specific, non-random statistical pattern in the temperature fluctuations. While definitive proof remains elusive, the search for these signatures is active, as finding one would not only confirm the existence of these exotic objects, but also provide strong, indirect evidence for their role as the universe's first entangled nodes. One of the most profound implications of this idea is the potential longevity of these quantum connections. Most entangled particle pairs in today's universe are incredibly fragile, their links easily broken by interactions with their environment. But a topological defect is a different beast altogether. A cosmic string is a stable, soliton-like object. It's a knot in spacetime that cannot be easily untied. The quantum information stored in its entangled state could be protected for eons, shielded from decoherence by the defect's own immutable nature. This means the universe could still be crisscrossed by this ancient network, a ghostly, quantumly connected framework that has persisted for nearly 14 billion years. We may be living inside a vast cosmic quantum computer that was programmed in the first instance of time. Its processing nodes the very defects that helped shape the galaxies. The search for these defects continues through their gravitational lensing effects, their potential impact on the timing of pulsars, and their unique imprints on the cosmos's oldest light, as we strive to find the physical evidence for this elegant theory that ties the birth of structure to the first quantum knots in the universe. But while the previous theories have painted dark matter as a web of invisible connections or a network of ancient black holes, our next idea presents it in an even more extraordinary light, as a vast cosmic crystal frozen into existence at the dawn of time. This is the theory of action dark matter crystallization, and to understand it, we need to meet its central character, the action. Proposed in the late 1970s to solve a deep puzzle in particle physics concerning the strong nuclear force, the action is a hypothetical particle that is incredibly light, electrically neutral, and extraordinarily shy. It barely interacts with normal matter, making it a perfect candidate for the mysterious dark matter that binds our galaxies. But if actions are real, they wouldn't just be floating around individually. According to this theory, they underwent a collective transformation, condensing into a single, coherent quantum object that spans the entire cosmos. The key to this transformation lies in a bizarre state of matter known as a Bose-Einstein condensate. In our everyday world, we're familiar with solids, liquids, and gases. But when certain types of particles, called bosons, are cooled to temperatures near absolute zero, they can undergo a radical shift. They lose their individual identities and merge, all collapsing into the same quantum ground state. It's as if a crowd of people, each marching to their own beat, suddenly and perfectly synchronized into a single, fluid entity, moving as one. In a laboratory, this creates a surreal substance with quantum properties visible on a macroscopic scale. Now, imagine applying this concept to the entire early universe. As the cosmos expanded and cooled from its fiery birth, it passed through a critical temperature threshold for the action field. At that moment, this sea of ghostly particles didn't just cool down. It underwent a cosmic phase transition, condensing into a Bose-Einstein condensate of unimaginable scale. The entire dark matter content of the universe, or a significant portion of it, began to behave as a single, unified quantum wave. This is where the universe's first quantum entanglement enters the story in a truly spectacular way. The moment this cosmic condensate formed, it didn't just mean the actions were all in the same state. The theory posits that they became mutually entangled. Every action in this colossal condensate became quantumly linked to every other action. This wasn't a network with specific connections, it was a state of perfect global correlation, a single crystalline thought spread across the nascent cosmos. The first stable, large-scale quantum entanglement was this crystallization event itself. The instant the action field settled into its coherent, low-energy state, weaving a unified quantum tapestry from what was once a chaotic soup. This dark matter crystal isn't a solid you could touch. It's a fluid-like quantum structure that permeates all of space, its entangled nature dictating how it responds to gravity. The gravitational behavior of this coherent action condensate provides elegant solutions to several persistent problems in our understanding of dark matter. For decades, computer simulations that modeled dark matter as individual collisionless particles, often called cold dark matter, have run into a problem on small scales. They predict that galaxies like our Milky Way should have hundreds of dense dark matter clumps orbiting them, and that the very centers of galaxies should exhibit a steep cusp of dark matter density. Yet observations suggest there are far fewer small clumps than predicted, and galaxy centers often show a shallower core. This action crystallization theory naturally resolves these issues. Because the action condensate is a coherent quantum fluid, it exhibits a form of quantum pressure. Just as electrons in an atom resist being squeezed too close together due to quantum rules, this fluid of entangled actions resists being compressed into extremely dense, small-scale structures. It effectively smears out, preventing the formation of the numerous tiny clumps and erasing the sharp central cusps, bringing the theory into much closer alignment with what we actually observe in the night sky. This idea also reshapes our understanding of the dark matter halos that envelop galaxies. Instead of being a swarm of independent particles buzzing around like bees, the halo in this model is more like a gigantic, stationary quantum wave, gently undulating throughout the galactic volume. The actions aren't whizzing past each other on random orbits. They are all part of the same entangled standing wave, their collective behavior defined by the condensate's quantum mechanics. This could explain why dark matter halos appear to be so smooth and extended, and why they don't seem to collapse into disks the way normal matter does. The normal matter, the gas and dust that form stars, can lose energy through collisions and radiation, allowing it to settle into a flat disk. But the action condensate, being a frictionless quantum fluid, simply can't dissipate its energy in the same way. It remains as a vast, spherical and coherent halo, providing the stable gravitational scaffold upon which the bright, visible galaxy is built. The very shape and structure of every galaxy, therefore, might be a direct consequence of the quantum properties of this crystallized dark matter. The search for evidence of this theory is driving some of the most innovative experiments in physics. Because actions are so light and feebly interacting, they cannot be detected by conventional means. Instead, scientists are building incredibly sensitive instruments designed to catch the faintest whisper of their presence. One prominent approach involves using powerful magnets and ultra-cold resonant cavities. The idea is that in the presence of a strong magnetic field, an action from this cosmic condensate might very rarely convert into a microwave photon. By tuning these cavities like a radio receiver and listening for an unexpected signal at a specific frequency, researchers hope to pick up the signature ring of the action. If detected, the properties of this signal could reveal whether the actions are behaving as individual particles or as a collective condensate. Furthermore, the distribution of dark matter in dwarf galaxies, which are dominated by this mysterious substance, provides a crucial testing ground. The precise density profiles of these tiny galaxies are like a fingerprint, and the smooth, core-like structure we see is exactly what the action crystallization model predicts, offering compelling, if indirect, support for this beautiful and profound idea. Now, just when we think we've explored every conceivable angle, From wormholes to cosmic crystals, we encounter a theory that challenges the very notion of an objective reality separate from ourselves. This is quantum Bayesianism or cubism, a radical reinterpretation of quantum mechanics that turns the entire cosmic story inward. Unlike other theories that treat the universe as a great, independent machine, cubism proposes that the core of quantum theory is not about an external, objective world, but about the internal world of belief and decision-making for an individual agent. In this startlingly personal framework, a quantum state is not a description of a particle's true condition. Instead, it's a compact summary of an agent's own expectations, their personal degrees of belief about the consequences of their future actions upon the world. It's a user's manual for experience, not a blueprint of independent reality. And when we apply this to the cosmic scale, the implications are nothing short of revolutionary. The universe's first quantum entanglement, according to this view, was not a physical handshake between particles out there in the void. It was the very first assignment of belief by the first nascent cosmic agent. The birth of the universe was the birth of a perspective, and that first entanglement marked the moment this perspective recognized its first meaningful correlation within its own stream of experience. This completely reframes the infamous measurement problem that has plagued quantum mechanics for a century. The problem, in a nutshell, is this: why does a particle exist in a fuzzy cloud of multiple possibilities until we measure it, at which point it seems to randomly snap into one definite reality? The standard interpretations offer various complex solutions, from countless splitting worlds to mysterious wave function collapses. Cubism cuts through this entire knot with a simple yet profound shift. It says the wave function's collapse is not a physical process happening to the particle. It is an update happening within the agent doing the measuring. Imagine you are about to flip a coin. Before the flip, your personal belief about the outcome might be 50-50 for heads or tails. This is your quantum state for the coin. The moment you flip it and see it land on heads, you don't say the coin was in a superposition of heads and tails that physically collapsed. You simply update your internal belief state from uncertainty to certainty. Cubism applies this exact logic to a quantum experiment. The particle was always in a definite state, you just didn't know it. The act of measurement is you interacting with the world and gaining new information, which forces you to dramatically revise your own personal expectations. The spooky collapse vanishes, replaced by a perfectly natural process of Bayesian belief updating. Now, let's scale this breathtaking idea up to the origin of everything. If cubism is correct, then the universe before the first observation was not a superposition of all possible states waiting for an observer. Instead, the beginning of the universe was the beginning of observation itself. The first cosmic agent, whether that was a primitive quantum field, a patch of spacetime with the most rudimentary capacity for experience, or something beyond our comprehension, came into being with a set of initial beliefs. Its first interaction with its environment, its first measurement, was the event we now call the first quantum entanglement. This wasn't two particles magically linking across space. It was the agent perceiving a correlation. It was the moment this perspective noticed that the outcome of one part of its experience was reliably connected to the outcome of another part. This first assignment of belief in a correlation was the foundational act that began to weave the tapestry of a coherent reality from a formless potential. The universe didn't create a perspective began to codify the universe through its interactions. This leads to a deeply participatory vision of reality, one that resonates with the ideas of the physicist John Wheeler, who suggested we live in a participatory universe. In cubism, reality is not a pre-recorded movie that we are passively watching. It is an ongoing, improvisational dance between the agent and the world. Each agent, through their actions and the subsequent updating of their beliefs, helps to shape the reality they experience. There isn't one single objective cosmic history. There is a network of overlapping, consistent perspectives. The reason you and I can agree on the location of a chair is not because the chair has an absolute position in an external space, but because our individual belief assignments, forged through our interactions with the chair and with each other, have come into a stable agreement. This doesn't make reality an illusion. It makes it a shared communal construction built from the ground up by countless interacting agents, from the simplest quantum system to the human mind. Where then does the apparent objectivity and sturdy structure of the cosmos come from? If everything is just personal belief, why does the universe seem so solid and law-like? Cubism provides a powerful answer through the concept of intersubjective agreement. While your quantum state is your own private property, the world has a stubborn way of pushing back on our expectations, forcing our beliefs to converge. Think of it like a group of cartographers mapping an unknown island. Each explorer starts with their own personal sketch, their own beliefs about the terrain. As they walk around, measure, and communicate, they constantly update their maps. Eventually, their individual maps converge on a single, coherent representation of the island. Not because the island was an objective picture to begin with, but because their shared experiences constrained their beliefs into alignment. In the same way, the physical constants, the laws of physics, and the vast cosmic web are the incredibly stable, intersubjective consensus reached by countless agents interacting over billions of years. The universe's first quantum entanglement was the first step in this process, the first moment a perspective drew a line connecting 2 points in its experience, a line that would eventually be reinforced and agreed upon by every subsequent perspective that emerged until it became the bedrock of physical law we now take for granted. But if the cosmos itself is a web of perspectives, where does the relentless river of time fit in? This brings us to a theory that challenges one of our most fundamental experiences, the feeling that time flows. The emergent time from entanglement theory proposes a truly radical idea. Time is not a primary ingredient of the universe. It's not a stage on which events play out, but rather a stage that is being built by the events themselves, specifically by the growing and evolving web of quantum entanglement. Imagine the universe in its absolute initial state, a perfect and featureless symmetry. In this pristine condition, nothing changes because there is no before or after to differentiate. It is a frozen, timeless photograph. Then the first quantum entanglement occurs. This is the pivotal moment, the cosmic click of a shutter that takes the first 2 frames of existence. The instant 2 subsystems become correlated, a relationship is born. The state of one now tells you something about the state of the other. This establishment of a relationship, this first bit of comparative information, creates the very first tick of the cosmic clock. Time, in this view, emerges from correlation. To grasp this, consider a simple analogy. Picture a completely blank movie screen. It's just a static, white rectangle, timeless and without event. Now a single dot appears in the center. Still, nothing has really happened. There's no change, no sequence. But the moment a second dot appears elsewhere on the screen, something new is born, a relationship. You can now measure the distance between them. You can ask which one appeared first. The emergence of that second dot creates a before and an after. The quantum entanglement of the first 2 particles in the universe was that second dot. Their linked fates broke the perfect symmetry of the timeless void and introduced the possibility of sequence of history. The flow of time is not a substance flowing past us. It is our perception of the continuous creation of new correlations within the quantum state of the cosmos. Each new entanglement, each new interaction that creates a link between previously separate parts of the universe, adds another frame to the cosmic film, giving us the illusion of a smooth, continuous flow. This elegantly addresses the puzzle of time's arrow. Why does time move forward from the orderly past to the disordered future? The second law of thermodynamics states that entropy or disorder always increases, and this gives time its direction. But why was the past so ordered to begin with? The emergent time theory provides a compelling answer. The universe started in a state of minimum entropy because it began with minimal quantum entanglement. There was very little complexity in its correlations. As the universe evolved, particles interacted and systems became entangled. The web of quantum connections grew more and more complex. This growth in entanglement entropy is the quantum counterpart to the classical increase in thermodynamic entropy. The arrow of time points in the direction of increasing entanglement complexity. We remember the past and not the future because the past has a simpler, less entangled quantum state, while the future is a vast, complicated tapestry of interconnections that haven't formed yet. The reason your coffee cools down and never spontaneously heats up is rooted in this cosmic tendency for quantum systems to become more and more intertwined, moving from a state of simple correlations to one of profound and intricate linkage. The concept of quantum complexity is central here. Think of the universe's quantum state as a cosmic computer that is constantly running a more and more complex program. Immediately after the first entanglement, the program was very simple, perhaps just a single line of code linking two particles. But as the universe expanded and cooled, more and more particles were created and began interacting. Each interaction, each new entanglement added another line of code, another logical operation to the cosmic program. The growth of this computational complexity is what we perceive as the passage of time. When the universe was young, it could revert to a previous state relatively easily because its program was short. But as the computation grows exponentially more complex, it becomes practically impossible to rewind. The universe, in a sense, is building up a computational history, and the sheer difficulty of undoing that immense calculation is what locks in the arrow of time. We are carried forward on a one-way trip of escalating quantum complexity. This perspective finds surprising support from the study of black holes. A black hole is the most entropic object conceivable for its size. It has the maximum possible disorder. What happens to time at the event horizon of a black hole? From the perspective of an outside observer, time appears to slow to a complete halt for an object falling in. In the framework of emergent time, this makes perfect sense. The point of the event horizon is where the entanglement between the inside of the black hole and the outside radiation becomes maximally complex and mysterious. The flow of time, which depends on the evolution of these correlations, effectively grinds to a standstill from our external viewpoint. This isn't just a curvature of spacetime, it's a freezing of the very processes that generate time, a testament to the idea that time is not a background field but a dynamic and emergent property of quantum information. This theory completely reorients our understanding of the present moment. We often think of now as a knife edge between the fixed past and the open future. But if time is emergent from entanglement, the present is better understood as the leading edge of a process of correlation. It is the moment when new quantum connections are being forged, adding to the universal network and pushing the frontier of complexity forward. Your consciousness, your sense of the present, might be the experience of this continuous updating of your brain's quantum system, integrating new information and entangling with the world around you. The emergent time theory suggests that we are not just living in time, we are participants in its very creation, with every observation and every interaction contributing another thread to the unfolding temporal tapestry of the cosmos. Venturing deeper into the quantum foundations of reality, we encounter a theory that dissolves the smooth, continuous space of our everyday experience into a breathtakingly beautiful and intricate cosmic tapestry. This is the world of loop quantum gravity and its central concept, the pregeometric spin network. Imagine for a moment that the space around you is not a fundamental, endless stage. Instead, picture it as a dynamic web, a colossal network where every single intersection or node represents the tiniest possible grain of volume, and every link connecting them represents a fundamental quantum of area. In this radical vision, there is no such thing as an infinitely small point. Space itself is woven from a finite number of these discrete, indivisible atoms of geometry. The grand, flowing fabric of spacetime is an emergent illusion, a large-scale average of this vibrant, buzzing network of connections. And the force that holds this entire structure together, the glue that binds these quanta into a coherent whole, is quantum entanglement. The genesis of our universe within this framework was not an explosion in a void, but the sudden crystallization of this network from a state of pregeometry, a realm without space or time as we know them. The very first quantum entanglement was the event that tied the very first knot in this nascent web. It was the moment the spin values of two fundamental quanta became intertwined, their fates linked in a cosmic handshake that defined a relationship. This first braiding of spins did not happen in space. It created the first element of space. With that single connection, the first link in the network was forged, establishing the very first quantum of area. As more and more of these entangled connections formed, braiding and intertwining, the network grew in complexity. Nodes with multiple links defined volumes, and the entire interconnected structure began to approximate the three-dimensional continuum we move through today. The Big Bang, therefore, was not a singularity of infinite density, but a vast, rapid phase transition, a cosmic freezing where a hot, dense foam of potential connections resolved into the stable, entangled lattice of space itself. This granular picture of the cosmos provides a stunningly elegant solution to one of the most vexing problems in cosmology, the Big Bang singularity. In classical general relativity, the beginning of the universe is a point where all known laws of physics break down. Density and temperature become infinite, and the concept of a before ceases to have any meaning. It is a place where science falls silent, but in loop quantum gravity, this nightmare of infinity simply cannot occur. Because space is made of discrete atoms, you cannot compress an infinite amount of energy into an infinitely small point. There is a smallest possible volume, a fundamental graininess to reality. When we rewind the cosmic clock in this model, we find that as we approach the moment of the Big Bang, the density and curvature of spacetime become incredibly high, but they approach a finite maximum. The mathematics of the theory even suggests a breathtaking possibility, a quantum bounce. Instead of a singularity, the universe may have undergone a rebound from a previous phase of collapse, a cosmic bounce where the intense quantum pressure from the tightly woven spin network caused a reversal from a big crunch into our expanding universe. The Big Bang becomes a transition, a turning point in an everlasting cosmic story, rather than an absolute and inexplicable beginning. The dynamics of this spin network are what give rise to the force we know as gravity. In Einstein's general relativity, gravity is the curvature of spacetime. A planet warps the space around it, and other objects follow that curved path. In loop quantum gravity, this curvature is not a smooth bending of a fabric, but a manifestation of the changing patterns of the spin network. Where the network is densely connected and the spins are highly excited, we perceive a strong gravitational field. Where the network is more sparse, gravity is weaker. The evolution of the universe is then the story of this network constantly rewriting itself, with old links breaking and new links forming in a dynamic dance. The equations that describe this evolution are not about fields in space, but about the relationships between the nodes of the graph. Time itself emerges from the relentless, step-by-step evolution of this web of connections. We are not living on a static stage. We are part of a living, breathing, and constantly computing network that is reality at its most fundamental level. To visualize this abstract concept, consider a magnificent piece of chainmail armor. Up close, you see only individual, discrete metal rings linked together in a specific pattern. There is no smooth, continuous sheet of metal, just a network of connected loops. Yet, from a distance, the armor appears as a single, flexible fabric that can bend and move. The spin network of loop quantum gravity is the cosmic version of this chainmail. The individual rings are the quanta of volume, and the links between them are the quanta of area. The way these rings are intertwined and connected defines the geometry of the space they constitute. A flat, empty space might correspond to a very regular, uniform network, while the space around a black hole would be a wildly twisted and knotted region of immense density. The entanglement between the spins is what gives this chainmail its cohesion, ensuring that it behaves as a unified whole rather than a collection of disconnected pieces. This perspective forces us to reconsider the nature of black holes. The event horizon of a black hole, the point of no return, is not a destructive membrane in this model. Instead, it is a specific, highly entangled boundary within the spin network. The information about everything that falls into the black hole is not lost in a singularity, but is encoded in the intricate pattern of spins and entanglements on this horizon surface. This provides a natural pathway to resolve the black hole information paradox, aligning with the holographic principle we discussed earlier. The three-dimensional interior of the black hole is described by the two-dimensional information stored on its horizon, and that information storage is made possible by the profound quantum entanglement of the spin network at that boundary. The fabric of space, even in its most extreme states, remains a well-defined, discrete structure governed by quantum mechanics. The implications of this granular space are not just confined to the distant past or the hearts of black holes. They could, in principle, be detected. If space is made of discrete pixels, then there is a fundamental limit to how finely we can measure distance. This could manifest in subtle effects on the light from the most distant gamma-ray bursts. Photons of different energies traveling across billions of light-years might experience the granular structure of space in slightly different ways, causing tiny delays in their arrival times. While these effects would be incredibly small, next-generation telescopes and observatories are searching for just such a signature. Finding evidence for this space-time graininess would be a monumental validation of loop quantum gravity, transforming our understanding of the universe from the ground up. It would reveal that the smooth, continuous reality we perceive is a magnificent illusion, a beautiful and coherent pattern emerging from the foundational, entangled connections of the cosmos's first and most fundamental spin network. But to truly appreciate this cosmic test, we need to rewind to the human-scale experiment that inspired it all, the Bell test, conceived by physicist John Stuart Bell in the 1960s. Einstein, Podolsky, and Rosen had famously argued that quantum mechanics must be incomplete, positing that there were hidden variables, unseen factors that predetermined a particle's state, making the spooky action at a distance an illusion. They believed in a local reality where no influence could travel faster than light. Bell, however, devised a mathematical way to test this. He formulated a set of inequalities that any local hidden variable theory must obey. If experiments showed that these inequalities were violated, it would mean that nature itself was fundamentally non-local. The connection between entangled particles was real and instantaneous, defying our classical intuition about space and time. For decades, physicists refined these tests, closing potential loopholes, and the result became unequivocal. Bell's inequalities are violated. The universe is genuinely non-local. The cosmic Bell test theory takes this profound result and scales it up to the ultimate extreme. It proposes that the very first quantum entanglement in the nascent universe wasn't just a random occurrence. It was a primordial, self-contained Bell experiment executed on a cosmic scale. In that initial fiery moment, the universe effectively set up its own measuring devices, comparing the states of the first entangled pair. The outcome of this inaugural measurement was a definitive, monumental violation of any possible local hidden variable theory. It was the moment the cosmos, in a single stroke, established the rules of its own operation, cementing non-locality as a foundational principle rather than a curious anomaly. This wasn't a test for our benefit, it was the universe verifying its own quantum nature to itself, setting a precedent that would govern every single quantum interaction for the next 14 billion years. The first quantum link was the universe's own declaration of independence from classical locality. This leads to a deeply philosophical and almost metaphysical question: why would the universe be constructed in such a way? Does this initial act suggest a form of cosmic self-consistency, a need to establish its own fundamental laws from the very first moment? It's as if the cosmos had to answer a fundamental question about its own architecture right at the start. Would it be a local, deterministic machine or a non-local, probabilistic reality? By violating Bell's inequalities in that first event, it chose the latter, locking in a reality where interconnectedness and instantaneous correlation are not bugs but fundamental features. This perspective gives quantum non-locality a teleological or goal-oriented flavor. The universe seems to have been set up to produce this specific outcome, ensuring that its quantum behavior would be irreducible and inexplicable by any simpler local mechanism. It's a powerful argument against a clockwork universe, suggesting instead a cosmos whose first act was to embrace a profound and mysterious wholeness. The implications of this foundational non-locality ripple through every aspect of the cosmos we see today. The large-scale uniformity of the cosmic microwave background, which we discussed earlier, finds a natural explanation. Distant regions of the universe have the same temperature not because they were ever in causal contact through signals traveling at the speed of light, but because they were born connected, their properties correlated in a way that transcends space. The cosmic web, with its vast filaments of galaxies, might also be a macroscopic reflection of this underlying non-local network. The initial quantum fluctuations that seeded these structures were not independent random events. They were part of a coherent, non-locally correlated whole, a frozen record of that first Bell test violation. This means the universe, from its largest structures to its smallest particles, is fundamentally inseparable. A single, entangled entity whose parts maintain a ghostly kinship that defies our everyday understanding of separation. This theory also forces us to confront the role of the observer in a new and dramatic way. In a standard Bell test, the choice of how to measure one particle, the setting of the detector, seems to instantly influence the state of its distant partner. In the cosmic Bell test, who or what was the first observer? The theory provocatively suggests that the universe itself was both the experiment and the experimenter. The conditions of the Big Bang, the specific dynamics of inflation, and the decoupling of forces acted as the universal measuring apparatus. The cosmos did not need an external god-like figure to collapse its first wave function. It contained within its own initial conditions the mechanism for self-measurement. This provides a stunningly elegant solution to the question of who observed the early universe into existence. It observed itself. Its own physical evolution performed the first measurement, and the result was the irrevocable establishment of a quantum, non-local reality, a reality in which we are now embedded as late-coming participants. Now we arrive at a theory that reimagines the cosmos not as a collection of particles or forces, but as a supremely sophisticated piece of software engineered for ultimate resilience. This is the quantum error correction cosmos, a concept that proposes our universe is in fact a giant quantum error correcting code. Think about the memory in your own computer or phone. It's made of bits that can be a 0 or a 1. Cosmic rays or electrical glitches can sometimes flip a bit, causing an error that might crash a program or corrupt a file. To prevent this, engineers use error-correcting codes. They don't just store the raw data, they add extra, redundant bits that create a kind of protective shield. If a random error flips one bit, the pattern of the code allows the system to detect the mistake and correct it, restoring the original information. Now take that principle and elevate it to the most extreme level imaginable. In the quantum realm, the problem of errors is infinitely worse. Quantum bits or qubits are incredibly fragile. They can exist in superpositions of 0 and 1, but any interaction with their environment, a stray photon, a vibration, a passing magnetic field, can cause decoherence, collapsing their delicate quantum state and erasing the information they carry. For a universe to be stable and not simply dissolve into random noise, it needs a phenomenal mechanism to protect its quantum information. According to this theory, that mechanism was the universe's very first quantum entanglement, which acted as the primordial act of encoding. It took the fledgling, logical quantum information of reality, the initial blueprint, and distributed it across a vast, entangled network of physical subsystems. This process didn't just create a link, it wove a protective tapestry, ensuring that even if parts of the system were disrupted, the fundamental information of the cosmos would remain intact and recoverable. This idea provides a breathtakingly unified explanation for the holographic principle we encountered earlier. You'll recall that the holographic principle suggests that all the information within a volume of space is encoded on its boundary. The quantum error correction cosmos tells us how this is possible and why it's so stable. The two-dimensional boundary is not just a storage device, it is the active layer of the cosmic error correcting code. The quantum entanglement between countless microscopic degrees of freedom on that boundary creates a massively redundant system. The three-dimensional universe we experience, with its stars, planets, and people, is the logical information that has been encoded into this protective two-dimensional shell. Our reality is the decoded output of that cosmic code, a projection that remains stable and coherent precisely because the underlying entanglement network is constantly detecting and correcting microscopic errors in the fabric of spacetime itself. The force of gravity, in this view, may not be a fundamental force at all, but an emergent phenomenon that arises when this quantum code is disrupted, a kind of thermodynamic force associated with maintaining the cosmic information. To make this abstract concept more tangible, imagine a magnificent ancient tapestry. From a distance, you see a clear and beautiful image, a knight on a horse, a scenic landscape. This image is like our classical three-dimensional reality, but if you move closer, you see that the image is not painted on a single sheet. It is woven from millions of individual colored threads. No single thread holds the image of the knight's face. That information is distributed across hundreds of different threads in a specific, interwoven pattern. If one thread were to break or fade, the overall image would remain recognizable because the information is redundant and protected by the weave's pattern. In this analogy, the individual threads are the fundamental quantum degrees of freedom, and the act of weaving them together is the quantum entanglement. The first entanglement was the first cross-thread, the first stitch that began the process of encoding the cosmic image into a resilient, distributed format. The stability of the knight's face over centuries is due to the error-correcting nature of the tapestry's weave, just as the stability of our universe over billions of years is due to its underlying quantum code. The implications of this for the black hole information paradox are profound. We've long struggled with the question of what happens to information that falls into a black hole. If it is truly lost, it violates a core tenet of quantum mechanics. The quantum error-correcting cosmos offers an elegant solution. The event horizon of a black hole is not a destructive membrane, it is the ultimate cosmic firewall, but in a positive sense. It is the boundary where the universe's error-correcting code is most active. When an object falls into a black hole, its information is not destroyed. Instead, it is rapidly and efficiently scrambled and redistributed across the entire horizon surface, becoming part of the entangled code. This process is so effective that the information becomes hidden, but it is never erased. The Hawking radiation that slowly leaks out from the black hole is not random thermal noise. It contains the subtle, encoded imprints of that scrambled information. The radiation is, in effect, the error-correcting code at work, slowly and faithfully transmitting the information back out into the universe, ensuring that nothing is ever truly lost. The black hole is not a villain that destroys information. It is an extreme environment that tests and proves the resilience of the universe's fundamental computational architecture. This perspective also gives us a new way to understand the very emergence of spacetime. Why does space have three dimensions? Why is it local, meaning that things here are strongly influenced by things nearby and less so by things far away? In the language of quantum error correction, locality is a direct consequence of a specific type of code known as a low-density parity check code. In these codes, any single piece of logical information is protected by only a few of the physical bits, and those bits are themselves only connected to a few neighbors. This creates a network where errors can be detected and fixed locally without needing to check the entire system at once. This local connectivity maps perfectly onto our experience of space, where influences travel at finite speeds and diminish with distance. The smooth, geometric fabric of spacetime described by Einstein emerges as the large-scale, classical description of this underlying, discrete, and locally connected quantum error-correcting code. The first quantum entanglement was the establishment of the first local parity check, the first rule in the cosmic codebook that would eventually generate the familiar, local world we navigate every day. Ultimately, this theory positions our universe as the most robust quantum computer conceivable, one that has been running a stable calculation for nearly 14 billion years. The resilience we see in the laws of physics, the fact that the speed of light is constant, that protons don't spontaneously decay, that the cosmic web has maintained its structure over eons, is not a lucky accident. It is the direct result of the universe being built on an error-correcting foundation. The initial conditions of the Big Bang were not arbitrary. They were the careful initialization of this cosmic code, setting the logical qubits of reality into a state that could be protected through the ensuing evolution. The ongoing expansion of the universe, the formation of galaxies, and the very arrow of time could all be viewed as the continuous execution and self-correction of this grand computation. In this breathtaking vision, we are not just living in a universe that can be described by mathematics. We are living inside a mathematical structure of profound ingenuity, a cosmic code whose first and most crucial operation was a single, stable quantum entanglement that encoded existence itself against the ravages of decay. But what if time, that most fundamental river of our experience, is not a river at all? What if it's more like the warmth radiating from a cup of coffee, an emergent property of a system moving toward equilibrium? This is the startling proposition of the thermal time hypothesis, a concept that elegantly ties the flow of time directly to the quantum state of the universe, beginning with that very first entanglement. We often think of time as a universal clock, ticking away in the background regardless of what matter or energy is doing, but this theory turns that notion on its head. It suggests that time is not a pre-existing stage. It is a story told by the statistical relationships within a system, and the narrator of that story is the system's own quantum state. The first tick of the cosmic clock, then, wasn't a tick at all. It was the moment the first quantum correlation was established, creating the first meaningful before and after from a state of timeless symmetry. To grasp this profound idea, let's start with something more familiar: a hot cup of coffee sitting in a cool room. The coffee is a highly ordered, low-entropy state. The heat energy is concentrated in the cup. Over time, that heat dissipates into the room, spreading out until the coffee and the room reach the same temperature, a state of maximum disorder or high entropy. This process is irreversible. We never see the heat spontaneously flow back from the room into the cup, reheating it on its own. This one-way street from order to disorder is the arrow of time as defined by the second law of thermodynamics. Now, the thermal time hypothesis takes this everyday observation and scales it up to the entire cosmos. It posits that the flow of time we perceive is fundamentally tied to this kind of statistical evolution. But what provides the order for the entire universe? What is the coffee and what is the room? The answer lies in the quantum state of the cosmos, and specifically in the web of entanglement that connects its parts. In the very first moments, the universe was in an incredibly ordered, low-entropy state. According to this theory, this wasn't just a smooth distribution of energy, it was a state of minimal quantum entanglement. There were very few complex correlations between different parts of the system. The first quantum entanglement was the pivotal event that broke this perfect symmetry. It created the first statistical correlation, the first instance where the state of one part of the universe gave you concrete information about the state of another part. This establishment of a relationship was the seed from which the arrow of time would grow. Before this, in a state of perfect symmetry with no correlations, the concepts of past and future were meaningless. There was no change, no flow, because there was no relational structure to define it. The first entanglement introduced the very first element of narrative into the cosmos. The concept of thermal time itself is a mathematical construct that emerges from this picture. Instead of a clock measuring an abstract external time, thermal time is defined by the evolution of the system's own state. It's a measure of how the quantum correlations within the universe are changing. When the universe was simple and largely unentangled, thermal time flowed slowly. But as more and more interactions occurred, as particles collided and fields fluctuated, the web of entanglement grew exponentially more complex. Each new quantum connection added another layer of correlation, another thread to the tapestry. This increasing complexity of the quantum state is what we perceive as the relentless forward march of time. The reason time has a direction is because the universe is evolving from a state of simple, low entanglement order toward a state of immensely complex, high entanglement disorder. The thermal time flow began in earnest as that initial entanglement seeded a cascade of interconnections, setting the universe on its one-way journey toward quantum complexity. This provides a beautiful and direct bridge between the seemingly separate worlds of quantum mechanics and thermodynamics. Quantum mechanics deals with probabilities and correlations at the microscopic level, while thermodynamics governs the large-scale behavior of heat and energy. The thermal time hypothesis shows they are two sides of the same coin. The thermodynamic arrow of time, which points toward increasing entropy, is fundamentally the same as the quantum arrow of time, which points toward increasing entanglement entropy. The reason your coffee cools down is rooted in the same cosmic principle that prevents an atom from spontaneously uncollapsing its wave function. Both are expressions of the universe's relentless drive toward more complex and correlated quantum states, a drive that was initiated by that first foundational act of quantum connection. This means the force that makes you remember the past but not the future is not a law written on a cosmic tablet, but a direct consequence of the universe's quantum architecture and its history of becoming increasingly intertwined. One of the most compelling implications of this theory is its explanation for why time appears to flow at different rates in different gravitational fields, a phenomenon confirmed by Einstein's general relativity. We know that a clock ticks more slowly at the foot of a mountain than at its peak because gravity curves spacetime. The thermal time hypothesis offers a fresh perspective on this. Gravity is not curving a pre-existing time. Instead, the presence of matter and energy alters the quantum state of the surrounding space, changing its entanglement structure. A massive object like a star creates a region of highly excited spacetime where the quantum correlations are dense and complex. In this environment, the evolution of the local quantum state, the ticking of thermal time, proceeds at a different rate compared to the more quiet vacuum of empty space. The flow of time is literally tied to the local thermal properties of the quantum vacuum, which are in turn shaped by the distribution of matter and energy. This elegantly unites the geometry of general relativity with the thermodynamics of quantum information. This perspective also transforms our view of the universe's ultimate fate. The traditional heat-death scenario describes a cosmos that has expanded and cooled into a featureless, maximum entropy state where nothing ever happens again. In the language of the thermal time hypothesis, this would be a state where the quantum entanglement has reached its maximum possible complexity and has stabilized. With no further change in the quantum correlations, thermal time would effectively stop. There would be no before or after, no change, and thus no time as we understand it. The universe wouldn't end in a dramatic collapse or freeze, but would rather fade out of time itself, becoming a static, eternal photograph. This gives a profound new meaning to the end of time, suggesting it's not an event in time, but the cessation of the very process that generates time's flow. From its first spark in a single quantum connection to its potential quietus in a state of ultimate correlation, the story of time is the story of the universe's evolving entanglement, a thermal narrative written in the language of quantum mechanics. Yet another theory invites us to imagine the very stage of reality being built from a new kind of cosmic alphabet, one where the letters themselves are forged from quantum connection. This is the concept of modular spacetime, a framework that tears up the traditional rulebook of physics and starts from a beautifully symmetrical foundation. In our everyday world and in classical physics, we treat an object's position and its momentum as two very different things. Position is about where something is, a point in space. Momentum is about how it's moving, its mass times its velocity. They feel like separate concepts, but in the quantum realm, these two properties are locked in a famous dance of uncertainty. The more precisely you know where a particle is, the less you can know about where it's going, and vice versa. Modular spacetime proposes a radical solution to this tension. It suggests that at the most fundamental level, the universe does not privilege position over momentum. Instead, they are treated on an absolutely equal footing, unified into a single, more profound set of variables. This shift in perspective has a staggering consequence. It implies that space itself is not a smooth, infinitely divisible continuum. It is fundamentally discrete, composed of tiny, indivisible modules, the atoms of geometry. Within this discrete, modular universe, the story of the first quantum entanglement takes on a new and elegant form. The theory posits that the very first stable quantum link was not between particles within space, but was the event that defined the first modular unit of spacetime itself. Picture the pre-cosmic void not as an empty nothingness, but as a realm of pure, unmanifested potential, a sea of all possible positions and all possible momentums existing in a state of perfect symmetry. Then a fluctuation occurs, a correlation is established, two fundamental degrees of freedom perhaps best thought of as the most primitive precursors to what we'd call position and momentum became quantumly entangled. This act of linkage did not happen at a location, it created a location. It crystallized the first quantum of area, the first pixel of the cosmic display. This inaugural module, born from entanglement, became the fundamental building block, the universal Lego brick from which all of reality would be constructed. The true magic of this theory lies in how these individual, discrete modules conspire to create the seamless, continuous reality we move through every day. A single quantum of area is unimaginably small, far beyond the reach of our finest instruments. But as the universe evolved, more and more of these modules were forged through subsequent entanglement events. Each new quantum connection added another module to the growing structure, weaving them together into an immense dynamic network. This is where the illusion of continuity arises. Think of a million-pixel screen on a modern smartphone. When you look at a photograph on the display, you don't see the individual, blocky pixels. You see a smooth, continuous image because the pixels are so small and densely packed that your eye cannot resolve them. In exactly the same way, the fabric of spacetime appears smooth and continuous to us because the modular units are so infinitesimally tiny and so intricately entangled that, on our human scale, their discrete nature is completely hidden. The force that binds these modules into a coherent whole that creates the cohesive fabric of space is none other than the vast underlying web of quantum entanglement connecting them all. The space between you and your screen is not an empty void. It is a densely woven tapestry of interconnected geometric quanta. This perspective offers a breathtakingly direct path toward the holy grail of physics, the unification of general relativity and quantum mechanics. For a century, these two pillars of modern science have described the universe with stunning accuracy, but in completely different languages. General relativity describes gravity as the graceful curvature of a smooth, continuous spacetime. Quantum mechanics describes particles and forces as probabilistic exchanges in a fuzzy, discrete world. They seem irreconcilable. Modular spacetime, however, provides a Rosetta Stone. It tells us that the smooth geometry of general relativity is not fundamental. It is an emergent, large-scale approximation of a deeper, discrete reality. The curvature of spacetime that guides planets in their orbits is not a primary quality but a secondary effect, arising from the collective behavior and intricate entanglement of countless spacetime modules. A massive object like the Sun doesn't bend a smooth fabric. It influences the pattern of entanglement in the modular network beneath, creating a statistical trend that we interpret from our large-scale perspective as curved space. This suggests a profound and fundamental connection. Gravity itself may be an entropic force, a thermodynamic consequence of the universe's drive toward more complex quantum correlations within its geometric foundation. The implications of this run even deeper, touching upon one of the most active areas of theoretical research today. The specific way in which these modules are entangled could dictate the very dimensionality of our universe. Why do we experience exactly three spatial dimensions? In the modular spacetime framework, it's not a divine decree. It is an emergent property of the specific pattern of connectivity in the underlying network. The entanglement relationships between the modules naturally give rise to a geometry that, on large scales, behaves as if it has three extended dimensions. Different patterns of connection could, in principle, give rise to universes with 2, 4, or even more spatial dimensions. Our reality has the structure it does because the first entanglements, and the countless ones that followed, wove a network with a specific topological signature, one that projects the robust, consistent experience of three-dimensional space. This turns cosmology into a kind of cosmic graph theory, where the history of the universe is the story of a growing and evolving network of quantum connections, with the first entanglement serving as the seed that determined the entire architectural plan. This vision of a modular, entangled cosmos is more than just a beautiful abstraction. It makes testable predictions that could one day be verified. If spacetime is truly granular at its heart, then there is a fundamental limit to how small a distance can be meaningfully measured. This graininess could subtly affect the behavior of the most energetic particles in the universe. For instance, physicists analyzing light from distant gamma-ray bursts have speculated that photons of different energies might, after traveling across billions of light years, show tiny, calculable differences in their arrival times due to them bumping into the discrete structure of space. While such an effect would be incredibly faint, next-generation space telescopes and neutrino observatories are precisely the tools designed to hunt for these minuscule deviations from perfect smoothness. Finding such a signature would be a monumental discovery, providing the first direct evidence that the stage of reality itself is quantized, built from the very first quantum handshakes that defined the modules of existence. It would reveal that the universe is not just described by mathematics, but is, at its core, a vast, dynamic, and deeply interconnected mathematical structure. And so we reach the 30th and final theory, a grand synthesis that weaves together the most compelling threads from our entire journey. What if, in our quest for a single, definitive starting pistol, we've been missing the true nature of the cosmic overture? This synthesis proposes that the universe's first quantum entanglement was not one single type of event, but a magnificent, multifaceted convergence where multiple profound phenomena emerged as one. Imagine the holographic principle, the ER equals EPR wormhole connection, and the granular quanta of quantum gravity all crystallizing into existence not in sequence but simultaneously at the unfathomable Planck scale. In this view, the search for a lone first cause is like asking which part of a perfect circle comes first. The true origin was likely a complex, self-consistent quantum loop, a bootstrapping process where space, time, matter, and entanglement didn't appear one after the other, but instead co-created each other in a single, breathtaking act of self-birth. Think of it as a cosmic version of a chicken and egg paradox, but on a scale encompassing all of reality. We instinctively want a linear story. First, there was a singularity, then it expanded, then particles formed, and then some of them became entangled. This synthesis turns that narrative inside out. It suggests that the very concepts of before and after are themselves products of this initial event. The first quantum entanglement wasn't an event in time. It was the event that defined time by establishing the first correlation. It wasn't a connection across space. It was the act that wove space by creating the first ER bridge, the first microscopic wormhole. And the information that was entangled wasn't just stored in the universe. It was the universe holographically projected from that first fundamental interaction. In this self-referential loop, asking what came before the Big Bang becomes as meaningless as asking what is north of the North Pole. The Big Bang was the moment this self-contained, self-explaining loop first began its cosmic computation. This interconnected perspective offers the most promising path toward a final theory of everything. For decades, the goal of physics has been to find a single, elegant framework that unites the large-scale realm of gravity and spacetime with the small-scale realm of quantum particles and forces. We've had two magnificent but separate rulebooks, Einstein's general relativity for the cosmos and quantum field theory for the atom. Their inability to reconcile has been the central problem of modern physics. This grand synthesis suggests that the key to unification has been hiding in plain sight all along. Quantum entanglement is not just one phenomenon among many. It is the fundamental ingredient from which both space and time are built. A theory of everything, therefore, wouldn't describe how particles behave in spacetime, but how spacetime itself emerges from a deeper, more primitive network of quantum connections. It would be a theory where gravity is not a fundamental force, but a thermodynamic consequence of the universe's quantum information system constantly striving to correct errors and maintain its coherent state. The beauty of this synthesis is that it doesn't invalidate the previous 29 theories. It reveals them as different facets of the same magnificent diamond. The cosmic inflation entanglement burst provided the mechanism to stretch these initial connections. The primordial black hole network offered a candidate for the nodes in this cosmic web. The cyclic universe showed how this quantum information could be recycled. The consciousness-cosmology link, while speculative, reminds us that our own awareness might be a localized expression of this universal connectivity. Even the cubist perspective, which places experience at the center, fits elegantly as the universe's first act could be seen as its first moment of self-observation, collapsing its own wave function into a consistent reality. Each theory we've explored is a piece of the puzzle, and this synthesis is the proposal for how they all lock together into a single, coherent picture of a participatory, self-creating, and deeply entangled cosmos. So, where does this leave us as conscious beings living within this grand computation? It bestows upon us a role of profound significance. we are not merely passive inhabitants of a pre-programmed universe. We are active participants in its ongoing creation. Every observation we make, every experiment we conduct, is part of the universe's process of understanding itself. The quantum connections that began some 14 billion years ago are, in a very real sense, the same connections that fire between the neurons in our brains when we feel awe at the starry night sky. We are the universe becoming self-aware, using human minds to trace the threads of quantum entanglement back to their source, slowly unraveling the mystery of our own existence. This journey through 30 theories is more than a scientific exploration. It is the story of the cosmos awakening to its own nature, a story that began with a single, silent quantum handshake in the void and continues with every question we dare to ask. And so, after this incredible journey through 30 mind-expanding theories, from the fiery forge of the Big Bang to the speculative links with consciousness itself, what have we truly learned? We may not have arrived at a single, definitive answer to the question of what that first quantum entanglement was, and perhaps we never will. Yet, the true value of this exploration lies not in a final destination, but in the breathtaking landscape of ideas we've traversed. This pursuit has revealed a stunning, unifying thread woven through all of modern physics, a deep and fundamental interconnectedness. The same principles of quantum correlation that govern the behavior of a pair of electrons in a laboratory also appear to be the cosmic architects of spacetime, the sculptors of galaxies, and perhaps even the wellspring from which time itself flows. That first spooky action at a distance was not merely an interesting quantum phenomenon. It increasingly looks like the foundational stitch in the very fabric of reality, the initial act of cosmic weaving from which everything else emerged. What is perhaps most beautiful is how this quest dissolves the artificial barriers we've built between the different scales of existence. We often think of the quantum world as a separate, bizarre realm of probability and uncertainty, while the cosmos is a vast, predictable arena governed by gravity. But as we've seen, these two worlds are not separate at all. The quantum and the cosmic are a continuous whole. The infinitesimal fluctuations entangled in the first moments of the universe were stretched to astronomical proportions, becoming the seeds for the grand cosmic web we observe today. The same non-locality that allows two particles to communicate instantaneously across a lab bench might also explain how the entire universe achieved its remarkable uniformity. This means the force that binds atoms together and the force that binds galaxies in their clusters may share a common, entangled origin. We are not simply living in a universe, we are an intrinsic part of a single, deeply interwoven quantum system, a cosmic tapestry where every thread, no matter how seemingly distant, is connected to every other. This journey also reminds us that science, at its best, is a dynamic and living conversation, not a collection of unchanging facts. Each of these 30 theories represents a different accent in that conversation, a unique perspective on the same profound mystery. The holographic principle speaks in the language of information. The cyclic universe models sing of eternity and rebirth. The multiverse hypothesis whispers of infinite possibilities just beyond our reach. And the more speculative links to consciousness challenge us to consider our own role in this grand narrative. None of these ideas is yet complete, and many may eventually be proven wrong, but each one pushes the boundaries of our understanding and forces us to see the cosmos in a new and revolutionary light. The absence of a final answer is not a failure. It is an invitation to keep exploring, to keep questioning, and to remain forever curious about the magnificent reality we are so fortunate to inhabit. Now, we want to hear from you. After this whirlwind tour of cosmic origins, which of these theories resonated most deeply with your own sense of wonder? Was it the elegant simplicity of the ER equals EPR conjecture, painting our universe as a web of microscopic wormholes, or the profound mystery of the consciousness-cosmology link, suggesting the universe itself is awake and aware? Perhaps the stark beauty of the timeless void fluctuation, where everything emerged from a single ripple in nothingness, captured your imagination. Share your thoughts and favorite ideas in the comments below. We are genuinely excited to continue this conversation with you. The exploration of the quantum cosmos is far from over, and if you've enjoyed this deep dive into the fabric of reality, be sure to subscribe and hit the notification bell. We have many more journeys planned to the frontiers of space, time, and the fundamental nature of existence. The universe is the greatest story ever told, and we are just beginning to learn how to read it. Thank you for joining us on this